Hello, everyone. Welcome to DevFest West Coast 2020. Hello, everyone. Welcome to West. So, as always, this is how we start a GDG event, is by talking about the community guidelines. We are an inclusive community that welcomes everyone, and please be excellent to each other. So this is a joint event by GDG, GDE, and TensorFlow communities, by GDG Seattle, Portland, San Francisco, Silicon Valley, and the TensorFlow Northwest, also by a few of us machine learning GDEs. So some of you have been to our GDG Seattle events before. GDG Seattle has 7,000 plus members, and we have monthly tech talks, workshops, study jams, and DevFest. And here's just some of the pictures from past events. So here's GDG Portland and GDG Cloud San Francisco, and also GDG Silicon Valley in TensorFlow Northwest. So here's today's schedule. About at 1 o'clock, we're going to start with our talks. We have 7 talks, and then we will wrap up about 5:15 p.m. Each talk is about 30 minutes long, some of which are 45 minutes. And then we're going to have raffle drawings at 2 o'clock, 3:30, and 5:15 p.m. During the talks, you can feel free to use these hashtags and DevFest 2020, DevFest West Coast 2020, DevFest Stories, and TensorFlow. So I have highlighted this one, the DevFest West Coast 2020, because that is the one that we actually use to do the raffle drawing. So the raffle drawings actually be based on your tweets on Twitter. So with that, let's get started with our very first talk.
Hey everybody, we will start at 1 p.m. But until then, just a quick overview. If all of you can chime into your comments about where you are joining in from today, that'd be great. We can see how or where people are joining in from. Awesome. Thank you, everybody, for sharing your details on comment. We see that we have people from everywhere around the world joining us here. Hello from folks from India, Portland. We see people from Seattle over here, and Sunnyvale, Santa Clara, SF as well, Vancouver. Hi, everybody. Glad that you could join us today. So for first, we have all of our agenda on DevFest West Coast. For the first talk, I have the honor to invite one of my friends, Hannes Happel. He's a senior machine learning engineer at SAP. He's also a fellow Google developer expert on machine learning. He also recently wrote an amazing book on building machine learning pipelines, which is now available for sale as well from O'Reilly. So feel free to take a book, go order on Amazon. And yeah, for a short summary, I'm assuming for that book, here's Hannes. Go home.
Vikram, thank you very much for the very kind introduction, and also thank you for having me today to talk about TensorFlow Extended. And it's great to be part of that amazing DevFest West Coast 2020. Yeah, let's jump right into the presentation. So what I want to talk about in the next 30 minutes is how we can take our machine learning models we have trained so in our experiments, and how do we turn them into pipelines so we can use them consistently in products. Just real quick, as Vikram mentioned, I work at SAP. I'm one of those GDEs, as you can see in that photo here. And together with Catherine Nelson from SAP, we both co-authored the O'Reilly publication, Building Machine Learning Pipelines. And today's talk is a very, very, very brief summary, and some slides might be abbreviated, and we might rush through some content here. So if you want the complete deep dive, I highly recommend that publication. Before we get into all the TensorFlow Extended details, let's quickly talk about machine learning engineering. When we normally talk about machine learning in presentations, we talk about algorithms, we talk about new architectures. This is basically the orange, or the orange box here. So we talk about machine learning frameworks, PyTorch versus TensorFlow, et cetera, et cetera. But when we want to take those trained models into production, the ecosystem looks much bigger. So all of a sudden we have to take a look at how do we keep updating our models, how do we analyze the models, how do we serve them, things like this. And those topics is what we understand these days with the term machine learning engineering. So when I describe my job, I often say, like, it's sort of like the machine learning plumber. You take the data, you turn it into a model, you help with the training, and then I help with deploying those models and capturing the data from those deployments. But I'm not focusing on the actual ML code. That's what, in my opinion, data scientists do and what they're the experts in. But then when we take a look at, like, why do we need machine learning engineering? There's often the conception in the machine learning field that, hey, I train my models in my notebooks. Well, there's a couple things happening here. Yes, you get a trained model out, but there's no focus on reproducibility. There's no focus on traceability, which will become more and more important in the coming years. And we want to reduce the burden for data scientists. That's what I think the purpose for machine learning engineers is. We want to make it as easy as possible to update models, because if we, or data scientists, release models, we can't spend 2 hours each week for each model to update that and keep it up to date. That needs to happen automatically. And what I want to show in the next 30, 25 minutes is basically how can you do this with TensorFlow Extended. All right, so let's quickly talk about what happens to trained models in most situations. Well, sadly, they usually don't get deployed. Let's face it, because the whole ecosystem of machine learning engineering has been too cumbersome and complicated in the past, and a lot of data scientists have given up on bringing out their amazing work into a real-life scenario. There is always a funnel. So let's say you have 1,000 experiments. Maybe you tune 100 of those models, and maybe 10 of them get deployed. But we might miss out wonderful opportunities to contribute back to society with machine learning and help with like applications if the deployment or like the operation of those machine learning life cycles is too cumbersome. There are some other aspects. Some models do get deployed, but then all of a sudden we have a whole different set of problems. Those models experience data drift. The schema might change. So we train with one set of data, and then 3 months later, maybe the database schema changes, and all of a sudden our training data downstream changes as well. We see training serving skews. There's like complicated pre-processing steps. Often they get updated without updating the model. The whole retraining is really complicated. When I speak with other data scientists, I hear stories of like, yeah, we don't update models because it's just simply too expensive and it takes too much time. And then we have like the whole ecosystem of like deploying machine learning models when it comes to like, ooh, how can I reduce the latency of my predictions and things like this. So this is what we describe as the machine learning lifecycle. So basically, if you would draw it out in a very generic life cycle, so it always starts with the ingestion of the data. We validate the data. We pre-process or do some feature engineering there. We train a model. In some situations, also we tune our models. Then there's a very critical step, which I think often gets left out when we talk about machine learning life cycles. It's like before we deploy the model and after we train it, the model needs to be seriously analyzed and also validated. And then once the model is deployed, we really need to capture the feedback about the model, because that's our lifeline, and we can also use the feedback to generate more data. So that's why it's an endless cycle, as we'll see it. And as you can see, and as you can imagine, those systems are highly entangled. So meaning if you change some hyperparameters during your training, your model analysis and your model validation will look very different. You might have to validate it with different thresholds, and your serving might look different. So if you change one parameter, it has a whole downstream effect. So doing this manually will take a tremendous amount of time, and that's why the focus should be on automating those machine learning life cycles. And this is where TFX, or what we call TensorFlow Extended, is here to help. Basically, TensorFlow Extended provides you all the tools to automate your machine learning lifecycle. So if we take a look at this, this is basically the individual components. So we have like components in our machine learning pipeline. And here we start with like the data ingestion. We do some, again, data validation, pre-processing. Sometimes people do the data validation after the pre-processing as well. There are good reasons for that. But for simplicity, I've left it out here in that overview. We train our models, we validate them, and then we deploy them. And this all runs in the TensorFlow ecosystem. And then we can express those components and orchestrate those pipelines in various systems. And I'll talk about this in a couple of seconds here. But also, if you look at those components, which TensorFlow Extended is providing, so basically for each step you see in those blue boxes, you have the white boxes, which are the individual components you can use from the TensorFlow ecosystem to build your machine learning pipelines. And then you have the orange boxes, which are the standalone libraries from the TensorFlow ecosystem, which you can use for your pipelines. And some of those components are framework agnostic. That's so if you have a PyTorch model, you can also use that with those components. Yeah. As I said earlier, once you design your pipeline, you can orchestrate that pipeline and you can run it in various ways. You basically have 4 different ways of running your pipelines. The first one, you see the Jupyter Hub notebooks there. That's technically not a pipeline, but in the TFX ecosystem, it's called the interactive context. Basically, you can run the individual components and you can debug those components. But some people use that in a notebook just to string a pipeline together. And if it works, they export it towards Apache Beam, Airflow, and Kubeflow. There will be a talk right after mine where you get a wonderful deep dive into Kubeflow. So I highly recommend staying on, watch the talk by Carl, and you will find out all the details about Kubeflow. But what I want to stress here, if you don't have Kubeflow set up, or maybe you work in a company or in a project where you already have Apache Airflow, you can also orchestrate your machine learning pipelines with Apache Airflow. All right, let's take a quick look how we can run TFX in action. A couple of months ago, my colleagues and I at Concur Labs, we wrote this blog post at the TensorFlow blog of how we use BERT models in connection with TensorFlow extended pipelines. And the reason for implementing that as a TFX pipeline was A, we didn't want to update our model frequently, and B, we wanted to take advantage of TensorFlow Transform. In the interest of the time, I will not get into all the TensorFlow Transform details, but there are 2 blog posts with all the details. If you're interested in how we use it and why we use TensorFlow Transform for our BERT models, I highly recommend that blog post, as you can see here on that slide. But let me walk you through how we set up the pipelines. So again, first, any pipeline starts with the ingestion of the data. So here we have, we define our input data pipeline, and TensorFlow Extended has wonderful functionalities. One of the cool functionalities is you can ingest the data from a folder or from some cloud bucket. It could be GCP, S3, anything what Minio supports. And then you can split those data according to a ratio you set. It doesn't need to be a double split, so you can say, you can also have like an extra test set. It's totally up to you. It's highly configurable. But this split will be then considered in the pipeline for your training and for your validation and potentially your testing. And then once you have all the inputs and outputs configured, you can ingest the data. And for that purpose, TensorFlow Extended provides you numerous components. So in this case, we're loading TF record files we already pre-processed. This is a very generic import here. The reason is also we use a public data set that was already available as TF records. There are components out there for BigQuery connections. We internally wrote like components for HANA connections. So if you're like an SAP customer, you can easily connect there. There's like numerous ways of ingesting the data. The wonderful thing I really want to stress here is under the hood, and you don't have to touch it. You actually don't see it. Under the hood, it is executing always everything on Apache Beam. So if you have like millions of files, Apache Beam will take care of the distribution of the data ingestion in that case. Once the data is ingested, we can do 2 amazing things. Number one is we can generate statistics of your data set. And here I want to stress, this is basically the one-liner is all you need to do. You basically point the statistics generator to your example data sets you just ingested, and then it will generate the statistics. And I'll show you an example here in a second. Once the statistics have been generated, you can also generate a schema. And I think a schema is often overlooked when we talk about machine learning pipelines or data pipelines. This will give you information of like, what are the columns? What are the features? Are the features dense? Are they sparse? What is, basically, if you have categorical features, what are the labels? And the wonderful thing in TensorFlow Extended is those information will be stored in a metadata store, and you can later compare against previous runs. So for example, if we train a machine learning model today, and we ingest new data, and let's say the data has updated or the schema has changed in the past, the pipeline would highlight us and say, hello, wait a second, there's a new column, or maybe there's a new label coming up in a categorical field. We can set thresholds where we can say, if data drifts in a certain direction, stop the entire pipeline and do not produce anything, but alert the data scientist. So here's an example of a visualization of the data we just generated. Also, and you will see this later on in the Kubeflow example from Carl, you can drill into the individual components, and some of those components have visualizations. So while the pipeline is running and continuously retraining your model from time to time, you get those amazing visualizations where you can drill into each feature, you can see the distributions, you can even compare the distribution and the data sets. There's a lot you can do with TensorFlow data validation. So once we have data not just ingested, but also generated the schema, and we have the statistics generated, then we can start diving into the feature engineering. And we can do this here with TensorFlow Transform. This needs its own talk to talk about TensorFlow Transform, so I just leave it with that. I just would say that you can express your data processing, pre-processing steps as TensorFlow ops. And because you do that as TensorFlow ops, you can build a graph out of this. And later on, when I show you how we export the model, you can attach the pre-processing graph together with the model graph from your trained model and export one artifact. This is a wonderful way to avoid a training serving skew when we serve machine learning models, and to always make sure that the pre-processing step is matching your latest machine learning model. So we just defined those TensorFlow ops. TensorFlow, the ecosystem, provides numerous wonderful manipulations. So if you're in the computer vision field, you can look into image manipulations from TF Images, or if you work with NLP problems, there's TF Text, where you get very powerful tokenizers for modern transformers, or like you need simple string transformations, you can always express them through TensorFlow ops these days. And if not, then under certain circumstances, you can also use TF functions to express your operations here. Once you have defined this, you save it in a module file, and in our case, we call this transform.py. And then we pass that to the transform component, where the component itself will look for the pre-processing fn function. That's basically the hook. And then it will apply those pre-processing steps to the ingested data. Once the data is transformed, we can start training our model. This is a way which was recently introduced in TFX, where we can use a generic trainer, which allows us to use Keras models. If you look at previous documentation, it always introduces, or we always had to use the TF estimator architecture. This is not the case anymore. I want to stress this. You do not have to train an estimator at this point anymore. But the wonderful thing is, because you have the pre-processing steps performed, we know the schema after the pre-processing, so you can easily load your machine learning models. That's basically, or your data, not the models, we're training them here. We can apply distribution strategies if we need to. Currently, TensorFlow Transform supports the mirrored strategy, because we can spin up individual external clusters to support more than the GPUs we have on hand, but that's at least, or that's so far a really good way of like distributing training capabilities. We load our models as usual. Like you define your models as through the functional API or through the sequential API. As long as it's a Keras or a TensorFlow model, that's totally fine. What I like to do is I prefer to pass in the transform output information, because then we can dynamically create the inputs to the model based on the previous step. The training and the serving, the training and the saving is exactly as we know this from previous TensorFlow or Keras models. We call fit, and then once we're done with the training, we save the model for future evaluations. And again, all those steps, we export them to a module file. In this case, we call this trainer.py. And then we pass this information to the component and say all the training information will be in that file. All right. We can also do the model analysis. the analysis steps are fairly lengthy. I really abbreviated this here. I highly recommend, if you're interested in like how to configure this in detail, take a look at the documentation from TFX or our publication. There's a lot. This is a really, really powerful component, because what you can do here is you can say, after the model was trained, evaluate the model with certain metrics. And the metrics are not just accuracy. This could be like an F1 score. It could be a precision recall. It could be whatever you want to define. And then you can take a look at specific slicing specs. So normally when you train a machine learning model and you run your validation set after every epoch, you would run it against the entire data set. And then you see like maybe an accuracy number or some loss, or maybe even an F1 score for this entire data set. But let's say you train a machine learning model and your data is like 80% from one country and 20% from another country, but you're trying to predict, like, let's say, restaurant reviews. You want to make sure that the model performance for country A is similar to the model performance for country B. But you can never see this from the model validation during the training. So this is where the model analysis becomes extremely powerful, because you can slice by countries and then make sure that the accuracy or the F1 score, or whatever metric they use, is similar by country. And then if maybe there's an outlier, you can investigate further or stop the deployment. This is extremely powerful. So really quick, as I said, you define your specs, you define your metrics, and then you can either slice against the entire data set, which would be very similar to your normal validation during the training, or you pick specific columns and slice by those columns and run the metrics against those columns. Super powerful. And again, this might be really small to read right now, but like it generates statistics, and those statistics can be visualized within your components when you execute them, for example, with Kubeflow pipelines. So we can drill into those components and then see the statistics afterwards. And the wonderful thing is also those statistics are preserved. So even if the model has shipped, we can always go back to our Kubeflow pipelines components. Sorry, and then investigate maybe in 2 months, how did the training actually look like? So if a customer comes in and says like, hey, this model is not performing as expected, we can see, did we miss something? We have all the metadata available here. We can also compare the different metrics, et cetera, et cetera. So that's all preserved. And then the last step in our short pipeline here is the model deployment. And the model deployment works hand in hand with TensorFlow serving. You actually you actually don't host it outside or coming out of the pipeline. You basically push the model into a location where a model server like TensorFlow serving or like Bento ML or an Onyx runtime setup could pick it up. So you can push those components. Sorry, you can push those models to an S3 bucket or to a GCP bucket, and TensorFlow serving could pick it up. But also, this pusher component can create like model serving endpoints in GCP, or what we have done internally, we have created components to create SageMaker endpoints if you're in the AWS environment. So this gives you a lot of flexibility of how you want to deploy your machine learning endpoints. But the wonderful thing is everything up to this point has to work out. It has to pass the data validation, it has to pass the training, it has to pass the model analysis. And the model analysis, and I forgot to mention this earlier, also compares against previous runs. So we can set the criteria that a model has to be better by X% than our previous models we have pushed out. And then once we define our pipelines, nothing has been executed so far. We can orchestrate them with the frameworks or with the libraries I put up here on this slide. So if you want a quick and easy orchestrated way of using your pipelines, you can use Apache Beam. It doesn't have a front end, but it makes sure that those components are orchestrated. If you already have ETL systems in your company or in your project and you use Airflow, you can easily orchestrate your pipelines with Apache Airflow. And then if you have Kubeflow running or Kubernetes running, it's very straightforward to set up Kubeflow, and you can orchestrate your pipelines with Kubeflow Pipelines. And that is a system which is specifically designed for managing machine learning pipelines, and you get all the wonderful benefits out of that. So there's one last step you need to do. You need to basically define which components go into your pipeline. You then define the configuration for your pipeline. So you say, where's your metadata store? Like, where do you store the information from each component, and so that the next component can adjust it? You can set configurations of like, how many GPUs do you want to use? How many gigabytes of memory do you want to claim in your cluster if you run it in Kubeflow, etc. And then you run your pipeline. And so what I want to highlight here is if you run your pipeline on Airflow or Apache Beam, it will immediately execute. If you run it with the Kubeflow DAG runner, it will basically convert whatever you configured in Python and convert it into an Argo configuration file, which you then can use either straight with Argo or with Kubeflow Pipelines, as Carl will demonstrate in the next talk. One thing I want to stress here is metadata is everything. I see a lot of talks about machine learning pipelines, and there's not a single word mentioned about metadata, but no component could connect to each other if we wouldn't have the metadata. So TFX provides you a metadata store. It'll take care of the communication between the components. You don't have to set which are the inputs, which are the outputs. That's what the components provide you. Even in the Kubeflow DSL, you sometimes have to stitch those components together. So if you want to simplify your life, the TFX DSL provides you all those pre-made components. If you want to configure your own custom components, TensorFlow Extended is highly flexible, so you can write your components from scratch, or you can inherit existing components, manipulate some executors. So there's a lot of flexibility for you in that system. Here's a quick example of how we would run this in Kubeflow Pipelines. This is an example from our book where we have a public data set of customer complaints, and we want to figure out which customer will complain or not. So it's basically in Kubeflow Pipelines, we converted our Python setup into an Argo run, Argo configuration. We loaded that into Kubeflow Pipelines, and then we can set up, this is a menu where you can set up weekly runs or daily runs, how often you want to trigger that. You can also trigger that through S3 buckets. There's a lot of ways you can trigger your model updates. And this is one thing I want to highlight here, is the lineage. That's the model lineage, which comes out of the metadata store. So once we have trained a machine learning model, and let's say we ship this model, we can always go back to the metadata store to say, okay, we shipped this model at this date. Let's retrace it. What was the input? Which model did we use? Which hyperparameters? Who signed off? We use like components where humans sign off on model deployments, and we can check which data scientists did the evaluation, what were the criteria, et cetera, et cetera. So this is a wonderful thing where we can say, this is also preserved, so we can always go back. That's our record of what led to that model. All right, I'm getting short here on time, so we quickly want to just summarize the reasons for TFX pipelines. As I said, the metadata store is there. It helps us to make our machine learning pipelines reproducible and also very consistent. We can automate the model updates. We get an audit trail, as I just showed you in the previous slide. There are ways where you can bring the human into the loop You can have a little, we have a little component in our setup where somebody in the Slack channel gets connected or gets contacted if a model reached a certain state and the pipeline evaluated the model and said like, hey, this looks great. Can a data scientist look over the results and sign off? And then we approve that or reject it via Slack. We can also automatically convert models to TensorFlow Lite and TensorFlow JS. I think this is with TensorFlow Lite becoming more and more powerful. This is extremely wonderful. We can train 2 models in parallel. One model goes to a machine learning server, and the other model is being shipped to the mobile team. We can tune as part of the pipeline, and then the best run, the hyperparameters of the best run will be used for a final training setup. We can do pipeline branching. So sometimes you want to have a canary model, and sometimes you want to have a test model with maybe slightly different hyperparameters. We can train them in parallel. And we have finally a way to do continuous model deployments. If you're interested in all the details, I rushed through a lot of details here. I highly recommend that publication. This is out this week, so it's brand new and everything is on up to date with the latest TensorFlow versions, TFX versions, and Kubeflow Pipeline versions. Yeah, with that, again, if you're interested in all the details of the example I showed you, check out the TensorFlow blog, where we explained in 2 parts the details of how everything works inside with BERT. And with that, thank you very much for taking the time. And yeah, there's a couple minutes left. I'm happy to take some questions.
Awesome. Thank you, Hannes. I don't see a lot of questions, but people mentioned something about data drift. Do you want to talk a little bit more about that? Or maybe a favorite instance of data drift that you have seen?
Sorry, the favorite what?
Instance of data drift happening in model or training instances that you can talk about?
Yeah, so it's often the case when you train a machine learning model and you put it out into the wild, people react to that model. And they learn how to tweak that model to their benefit, and that usually becomes visible in the data drift. So all of a sudden, certain labels don't show up anymore or show up dominantly, and then your entire model gets biased in a certain direction. And that's the wonderful thing with the TensorFlow data validation tool, where we can generate those statistics and compare them with every data ingestion. So I highly recommend that TensorFlow library.
Awesome, fantastic. Thank you so much, Hannes. Thank you so much for the talk. Looking forward to the book, actually.
Yeah, thanks for having me. It's quite a long journey. I'm looking forward to have the print copy for myself. So far, I've only seen digital versions. So
awesome.
Yeah, very excited about it.
Awesome. Thank you.
Thank you.
We will have next speaker joining in soon. Thank you, Hannes.
Thank you.
Everybody, we're ready to get started?
Yeah, so I'm Chris Thompson, representing GDG Cloud Portland, and as a machine learning engineer, my goal is always to design, automated, scalable machine learning pipelines. And this past year, Kubeflow 1.0 was released, and to address some of the challenges associated with that. So our next speaker, Carl Weinmeister, will talk about how you can implement Kubeflow Pipelines, which is a component of Kubeflow, to improve scalability and reproducibility in the machine learning process. So with that, I'll leave it to Carl.
Thank you, Chris. Appreciate it. And it was great to start with Hannes' talk this afternoon. I think he really set the stage with TFX, the TensorFlow extended set of components for machine learning. What we're going to talk about today is Kubeflow Pipelines, the runner that has a whole set of infrastructure around running your pipelines, tracking your experiments, and things like that. So let's go ahead and dive in. I'm going to share my screen, and we'll show a presentation and then a demo of Kubeflow Pipelines. So here we go. All right, so we're going to talk about building a reproducible ML workflow. That's really key here. When you're doing data science, as we all know, it's all about running experiments, trying new things. Eventually, though, you get to a certain point where you need to put things into production, and you need to make sure it works the same every time, that you've codified that complex set of steps from ingesting data to building models, pushing it into production, et cetera. And so we're going to go through how Kubeflow pipelines can help you with that. And we'll see how the TFX components, which Hans just spoke about, can fit into that. So we'll start talking about the challenges. I think we just covered some of the challenges in the previous talk, so I'll be brief about that. We'll talk about Kubeflow as a whole. We'll then really dive into the pipelines piece and then show a demo. So as we all know, when we starting a project, this is all relative, can be easy. Getting to that right level of accuracy can often, be very difficult, and many machine learning projects fail even in the early stages in terms of getting the right data to get the right result. But once you have that result, it gets even harder when you need to make sure that your model, which is needs to respond to changing data, changing requirements, updates, all kinds of things that your users trust. There's a whole new set of issues that come into play that make it harder. Some of the issues are things like a lack of continuous monitoring. You create your model, and we talked a little bit about data drift in the past talk. That the data coming in changes, and if your model's trained on a particular corpus of data, and then now you're seeing different data come in, it's very likely that your accuracy starts to kind of fall. And it's important that you have some way of knowing what that threshold is, where you want to get a notification, you want to start looking into it before it becomes an emergency. Another issue you might see is something called training serving skew, where this is often the case where the code that you use for training is different from the code that you use in your production system where the model's being used, in terms of processing the inputs and maybe doing some transformation steps. It's very possible that maybe you have some code that you push to one of the systems and not the other, or there's a variety of different types of scenarios like that that can pop up. And what happens is, it's another way of having issues in your production system. Training serving skew, something to look for. A key other aspect of your requirements is knowing what's the freshness of the model that I need. There's really a wide spectrum. If you're dealing with maybe, here's one extreme example, news data, but or maybe even you're working with an e-commerce site where the products are changing very often. You might need to rebuild models frequently. On the other hand, there are certain model types that are very stable that it's less often. So it's important coming into designing your pipeline, having a perspective on how often you'll need to create new models to meet those, the changing data and the accuracy that you need. Okay, so let's now talk about Kubeflow and how this can help. And the mission statement for Kubeflow here is in terms of making it easy for everyone, from data scientists who aren't necessarily infrastructure experts to machine learning engineers that maybe want to work more on the platform side and building the infrastructure and aren't necessarily working on the models, kind of a couple different stakeholders. And it's about the full life cycle, development, deployment, and management. So everything you need to do from end to end in machine learning. Focus on portability. Since you're building on top of a Kubernetes-based infrastructure, the pipelines that you build can work in these various different places, right? Whether it's cloud, on-prem, et cetera. And finally, because you're using Kubernetes, it has this fantastic way of distributing workloads across a cluster with pods that you can define. How much do you want to scale up or scale down? Monitoring tools. And often you see in a larger enterprise, the enterprise is using Kubernetes for software development and application development. So it's kind of nice to have one stack for DevOps that you're doing both development and data science on, just a smaller learning curve, fewer moving parts. And so Kubeflow is about bringing ML and Kubernetes together with some nice benefits for running your machine learning workflow. Now we're going to again focus on pipelines today, but it's important to understand what that Kubeflow foundation is. So all the things that go into Kubeflow you see on this slide, let's kind of start clockwise from the top. Jupyter notebooks for your development of your training code in any of the other code, maybe in Python, or your training operators. This is where you actually do the training. You instruct it what kind of maybe GPUs you want to use, what kind of framework you're using, and it will run the training job on the cluster. Then you see workflow building and pipelines, where we're going to focus today. Data management, there's also some capability around versioning, sharing the data. It's a key part of reproducibility as well. Moving around to tools, there's also a component in Kubeflow called Kotib that does your hyperparameter tuning, TensorBoard to do some debugging on your TensorFlow model, look at it in more detail. And then there are the Kubernetes tools for logging, monitoring, things like that. One of the new capabilities that was added to Kubeflow is metadata management. So there are APIs so that as you build a model, and as part of your pipeline, you can add information like, standard information, when was it built, what framework it was used, et cetera, and custom metadata that you can add to know more about the asset that was being built. And finally, the serving piece. Once you've built your model, why not use the Kubernetes cluster to serve it as well in the same infrastructure? So we'll talk about that briefly. So your Kubeflow is built in a side of it's deployed inside of a Kubernetes cluster, and so traffic coming in can either go to the central dashboard. There's a nice UI where you can see the pipelines, notebooks, TensorBoard, all kinds of different things there. There are the operators, and I'm going to show how you can kick off training jobs with those, and then the serving component where I'll talk briefly about the APIs. Then we'll get into pipelines. Okay, so if you want to get started with Kubeflow, if you never have before, if you're familiar with Kubernetes, you'll find that the commands and concepts are similar. So in the Kubernetes world, there's a utility called kubectl that's used for management of your Kubernetes cluster. There's KFServing for Kubeflow control. And you see here a few examples from the GitHub repo of different YAML files which define the services that I spoke about on the previous couple slides around the Jupyter server, serving, training, et cetera. This is what lays down the cluster and the necessary servers for various different platforms. And this is what it takes to install Kubeflow. And once you have Kubeflow going, I'll walk through a couple of the capabilities you have. The notebook server, so you'll can create various servers and then launch Jupyter Hub from that. For training, you can see where there are a variety of different YAML files. If you go to the Kubeflow GitHub repo, you'll see examples. Here is a PyTorch example on the left side. And what you see is where you would define the name of your PyTorch job. You would point it to, there's some standard container images with the training code, maybe some arguments that go into that container. And then you see, you can specify more details around things like, using a GPU or CPU, things like that within that YAML file. To launch a training job, here you're actually using the Kubernetes command here to go ahead and launch that operation and put that training code into the cluster, start up the pods with the the Python code that's going to run the training. And then if you want to check the status, there's a Kubernetes command that looks at the jobs running on the cluster and maybe filters it by a certain label to see what's happening there, and you can observe the training happening. Serving, basically, there's a framework called KFServing, where there are two different APIs, predict and explain, for your common use cases. Hans talked briefly about this concept of canary and sort of regular endpoints. So it supports that capability where you can have a standard endpoint that maybe gets 90+% of your traffic. Then maybe you're piloting a new model and you don't want to quite switch everybody over to it yet, but you want to test it. That's where you set up a canary endpoint. And so when you use KFServing, there's infrastructure available for that. And then, whatever endpoint you pick, there's an ability to transform the data coming into your endpoint. And then you could potentially have some code to provide an explanation, or if you have some interpretability code, and then you have the ability to actually use the model to create a prediction and then return the result back to the user. And so this is how you can create a REST endpoint in your cluster to accept input and serve your model in a scalable way and take advantage of Kubernetes auto provisioning and things like that. Okay, so now you've heard about the foundation of Kubeflow. Let's dive a little deeper into pipelines. So a pipeline is a set of steps that perform a machine learning task. So Kubeflow Pipelines is specifically built for machine learning workflows. It can do other general purpose workflows, but it's really aimed at solving the kind of problems that machine learning engineers have. So let's walk through an example of using the Kubeflow Pipelines SDK to build a pipeline. So what you would do is define your pipeline using these decorators. So you have your Python code, and then you can annotate the code with a few keywords that specify things like, I'm about to tell you that this is a pipeline. Maybe you add some metadata around it. Here's the name and description of the pipeline. And then you would have a method where this would define the parameters coming into your pipeline. Here we have some examples of maybe each time that the pipeline is run, you have some options like how many training steps, or maybe the data coming into the pipeline, and you can specify defaults so that each time it's run, you don't have to enter 7 different things if you don't want to, but you have the ability to override what's going into the pipeline. And then you define the steps in the pipeline by importing the KFP components package. And then what you're doing is to basically get access to a component. There's a load component from URL method in the KFP SDK, and that will point to a YAML file, and then you'll essentially have a definition of the component. You haven't instantiated it yet, but you kind of have access to the class. So here, the next step, what you're doing is you instantiate it, and then here, for instance, we have a copy component with the source and target directory. The next step you see here is how we would show dependencies between the components. So say we've got 2 components. How did we show, how does it know that one comes after the other? So here's what we're doing, where we're doing it explicitly. There's things like .after, .before, where you can explicitly specify the order. However, Pipelines is smart enough to know that, say you have an input parameter of one component that's coming from the output parameter of another, it will realize the order of operations, and you don't need to do this. So, so generally, you can just sort of define your components, and assuming the information kind of flows from one to the next, you don't have to do that. But in some cases, you might want to be more specific about parallelizing things, and that's where you'd use some of these different condition and type of control commands like that. Okay, so you've created your pipeline. How do you deploy it? So there is a compiler package, and you compile that Python code, into a tar.gz file, and then you can programmatically upload it, or here we're seeing in the UI where you upload the file or maybe point to URL, and then you'll see it in the dashboard. And when it imports, what you see on the right side is not an actual run of the dashboard, but you're seeing the graph of the different components and what the user would see during a full end-to-end run of the pipeline. And so really what I hope that comes across here is that you're able to define your pipeline in Python in the same language that the data scientists are using, with a couple small steps to compile it. Then you have it in a format that it can be executed in the Kubeflow Pipelines UI. And there are lots of reusable components already. So you see some of these different popular operations, extracting data from a database, transforming the data, so on and so forth. Even the TFX components that Hans talked to, there are components. If you go to GitHub, inside of the pipeline/components folder there, you'll see a nice set of arguments, what the component does, and so that you can pull that into the pipeline that you're building. So now we're going to talk a little bit about how Kubeflow and TFX can work nicely together. So if you're using the Kubeflow SDK that I just talked about, you can pull in any of the TFX components. There are Kubeflow SDK components that interface with the TFX component, so it's very easy to pull them in. There is also a TFX SDK that runs in Kubeflow Pipelines, and that's new, and that's something that I want to talk about more in the rest of the presentation. So you have two different approaches. You have the traditional Kubeflow Pipelines approach, where you can use Kubeflow components and TFX components. And now you have a TFX-centric SDK. And that's what you're seeing here on this slide, that you're seeing that there's two different approaches coming in, using on the left side from the top, the TFX SDK or the KFP SDK that we talked about. So depending on maybe if you're coming more from a TensorFlow perspective, where that's what your model's in, and you're familiar with TFX and you really want to embrace that ecosystem, it's you can use that directly. Maybe if you're doing more custom components or using some other frameworks, maybe you want to use the KFP SDK. But a couple different ways to do things. So now let's talk about how to build your own custom component. So we talked about building a pipeline and then the components that you could pull in off the shelf. Now, what if you wanted to build your own? How hard is that? So let's look at that. So I'm going to show you 3 slides which kind of walk through an example of training. We're not really getting really deep into the training code, but more showing the structure. Okay, so the first slide here, we're showing the YAML file. This is how we describe your component. This is where you name it, you say what the inputs are, the outputs are, and then a key link here is to the container image. Where is the code, where is the Docker container with the code that will run this component? So that's all this is. This is a descriptor. It's a YAML format. And this is, if you recall back a few slides ago, what we pulled from where we're trying to access a component. It would access this descriptor file. And then the next part is the Docker file where you define the image. So here's where you might base it off of a base image here, let's say TensorFlow. You maybe update it, you add a couple more packages to the base image, and then you define what the entry point is into the image, or what is going to be executed inside of that Docker container, maybe some model training code in this case. And then finally, let's look at what the model training code is. And this is kind of where everything comes together. Say you have a main method and you would parse those different arguments. These all match up to the inputs to that component. Where's your data, the number of training steps, all those kind of things. And then you have your code that does whatever you need it to do that's in this file or set of files. So that's it as far as building a Kubeflow component that goes into a pipeline. All right, so to summarize, what we saw is that Kubeflow is a cloud-native multi-cloud solution for ML. It allows for composable, portable, scalable ML pipelines. And if you have a Kubernetes cluster, you can run Kubeflow. I will also say, if you aren't super familiar with Kubernetes, there are some utilities that allow you to run a local instance of Kubeflow to get started. Some kind of smaller, mini KF and things like that. So very easy to get started with all the tools that have been built by the ecosystem. Okay. All right, so now let's spend a few minutes and kind of go over a demo here. All right, so what I'm going to show you is Kubeflow pipelines or implemented in Google Cloud, right? So there's lots of different ways to run it. What I'm doing is showing you a standalone implementation of Kubeflow pipelines where it's just the pipelines piece, not the whole Kubeflow platform. It's very easy to get started here. That's why I'm demoing it this way. I simply click new instance, and then I will be able to create the cluster with the Kubernetes cluster. I can specify a couple different options and click deploy, and then it will set it all up for me. So it's very convenient. I already have this going. It tells me, what the name of my cluster is, the version of KFP that's running, etc. So let's go ahead and click that link to open the dashboard. And let's walk through a few things. So here are the pipelines. And if you recall where I was mentioning before, uploading the pipeline, here's where you would do it. You can see that there are a few existing pipelines already here. For today's demo, I want to show you the TFX taxi tip prediction model. So this is a classification model. It uses all the TFX components, and it looks at a bunch of taxi data and tries to predict, is a taxi driver going to be tipped 20% or more, a binary classification problem. Here's what the graph looks like. I'm going to briefly change gears and show you how you find out more about this demo if you want to try it yourself. On TensorFlow.org, under TFX tutorials, you're going to find a demo on TFX and Cloud AI pipelines working together. And here you'll be able to run this demo. Okay, so let's go ahead and get started and dive a little deeper here. Oops, excuse me. So here is the pipeline. Let's go and look at experiments. So experiments are where we have a list of all the runs of the pipeline, right? So the pipeline is kind of like the class, the experiment is the instance. This is a run of the pipeline. So let's dive down into it. And you can see I've already run it, just for the purposes of today's demo. Always good to run things in advance. Everything ran smoothly. I think this will also show you another perspective on what we saw in Hannes's talk, where he showed you all the different components. Here's another end-to-end example. And what this does is first it uses the example gen component, and what this is doing is it's pulling from CSV files and doing the train test split and all that. And so you can see with each of the different steps in the pipeline, Kubeflow will show you the artifacts produced, what were the inputs and outputs to each step, even things like the log within the Docker container that was executed. And so that's all here. And then let's look at the next step. Okay, once we've done our train test split, here's the statistics gen component. And this is pretty cool because this component shows you, let me go a little more full screen on this. Your standard statistics, all the different features coming in, how many were there, what percent was missing, what's the mean, variance, understanding the data that's being used for your model. The next thing is schema gen. So this is another neat component. where this allows you to look at the training data and infer what this schema should be. So it tells you things like, okay, there's a company field, it's a type string, so on and so forth. That's all this information is here, and categorical variables, etc. It's going to create a schema out of that. Then here we're using a component called the example validator. And this kind of works together with the schema gen component in your test data and basically checks your schema and says, okay, let's put some new data against it and let's see how well it worked. And so what it does is it generates a report here, and you see some anomalies. So it looks like here that there were a couple new cab companies that weren't in the training data, which makes sense. So this is where you might say, well, my schema was a little strict. I don't actually want to say these are the only cab companies. And here's a case where our, I guess, a type of credit card wasn't in the training data, and that it came through in the test data. So it might be a revision to the schema. So this would be something that, back to the concept of training serving skew or drift, that you can kind of monitor looking at the example validator component. There's transformation, there's training. Training is where, let's see, if we go into the logs, you'd see things like with TensorFlow, looking at the loss and all that you can see within this as it's training. And again, as you're running real time, you'll see this unfold. You'll see sort of the green or red if it's successful. And so it's kind of fun to watch at times. And then the evaluator, and this uses TensorFlow model analysis. And what that does for you is it not only gives you your sort of standard accuracy statistics, but I think that this is an important feature is the ability to look at different slices of your data. So you want to look at your accuracy in terms of how it affects all of your users, right? Not just on the whole, but making sure that if we slice the data different ways, how are folks getting affected by that? So here for the taxi cab example, what's happening is it's looking at the taxi trips that start at 1 in the morning versus 9 in the morning, et cetera, and what are the accuracy. So you could see here, well, maybe because I have fewer trips at 1 in the morning, I have fewer training samples, my accuracy is a little bit lower. Maybe I need to collect a few more examples there. It does actually show you that example count. Okay, so my theory was correct here. We're kind of validating that. It just gives you a lot of great information about your training data and the accuracy by these different features. So this all sort of comes out of the box when you're using TensorFlow extended. Okay, I think I'm running a little short on time, but as Hannes mentioned, there's this concept of pushing your model to production once you reach a certain accuracy level that the evaluator will tell you about. All right, so just to summarize here, what we've talked about is using Kubeflow in a pipeline, how to use TFX with it, and I don't think I have time for questions, but maybe feel free to ping me. I'm on Twitter at kweinmeister or LinkedIn if you have any questions. Thank you.
Thanks a lot, Carl. That's awesome. Check out Kubeflow Pipelines. Also, they have great documentation if you have any other, technical questions or anything, but definitely ping Carl. He's one of the experts. Great opportunity to ask any questions you might have about that. But thanks, Carl. Really appreciate the talk.
I know we're running out of time, but I think we can ask a few questions. I actually put the questions on the screen. I don't know if you remember.
Yeah, a couple of them got answered. I think okay. I think that one of them though was asking. Well, one of them was asking about the demo. So obviously we saw where we can access that. Are there any other demos that you would recommend, Carl, besides the taxi cab demo like that? And can they find that in the same place?
Yeah. So if they go to the Kubeflow Pipelines repo, there's an examples folder that has a lot of great examples. I think the taxi cab example is the best one if you want to learn how TFX is used. But there are, I know that Kubeflow has a lot to learn. So sometimes people look at, there's very basic components too, like, hey, I just want to know the bare minimum of, if I want to create like a new container out of a few lines of code, how do I do that? So what I do think is helpful too is those simple tutorials that just give you like little tiny pieces of Kubeflow that will explain them bit by bit. So
yeah, I found when I was learning, it was a big undertaking. There's a lot to it. It's really, really useful though. As you get deeper, you'll find so many cool little things that aren't totally obvious right off the bat. So definitely play with it, I think, is the best course of action for learning. Cool. I think like I said, most of the questions got answered. And, but I encourage people to go play with Kubeflow Pipelines. I've been playing with it for a few months, and I really, really like it. So check it out for sure. Cool, Carl. Thank you so much.
thank you.
Thank you, Carl.
Thank you.
All right, so now it's raffle time. Okay. Oops, I didn't mean to start it just yet. Okay, let me just explain to you how it works. Actually, for those of you who have been to GDG events before, you might have seen this. Okay, that was not the real thing. Okay, we're not ready yet. Okay, so if you want to send one more tweet or something, remember it's hashtag DevFest West Coast 2020. So how this works is that we add all these people who actually posted with that hashtag, and then I'll just click on more, and I will click on import Twitter users. Okay, so we're gonna do that now for real this time. And actually, let me just clear this out. And we're gonna add everybody who actually tweeted with this hashtag. So you see everybody here. Well, I'm gonna just remove GDG Seattle here, and I think that's it, everyone. So are we ready? Let's see who get the first prize. Oh, I forgot to mention the prize. So the first prize is like a $25 DoorDash gift card. Okay, so this time it's for real. We have a winner. The previous was dry run. So I don't know who this person is. And the way it works is that if you could just, because we need your name and your email to send the gift card to you electronically. So I know you have come join through Eventbrite. Just send us your email through the Eventbrite contact organizer. Okay. So I'm gonna try run this again. The second one will be a Google Play card for $25 store card. Okay, so this is the second winner for the gift card, and we have it recorded here. So just contact us. All right. So next, we're gonna go on with our talks. I'm gonna see the next talk. Vikram and Recruits.
All right. So you might recognize this guy from earlier in the show. He's a speaker as well as an organizer. And today he's going to be talking to you about TensorFlow Hub in addition to AutoML. His name's Vikram, if you didn't pick that up earlier, and let's give him our attention.
Awesome. Thank you, Chris. Let's get started. Okay, so hi everybody. My name is Vikram. I'm a co-founder and tech lead at OmniLabs Inc. I am also a Google developer expert for cloud and machine learning. And today we'll be talking a bit about how we can help in your machine learning journey. So when we talk about machine learning journey, we generally expect, the expectation is that we will have the clean data the perfectly clean data available for us to build our machine learning models. And then we will have a great compute system where we will just upload all the data, write all the code, and train our model. And once we have all of that done, we will get an amazing robot for us, which will be our AI assistant that we can use everywhere. But the reality is sadly something else. In reality, we end up with really bad data, missing values, unknown values, null values, all sorts of things. We also have, when we spend so much time in cleaning up that data and actually start using it, we realize that most of the tools don't work together. The whole infrastructure around machine learning and machine learning engineering, the whole ecosystem is evolving slowly, but there are still tools which don't work well together with each other. So we have to perform our scripting magic and join all these different things together to build something out of it. And in the end, what we get is sometimes useful, but most of the time it just ends up as a zombie code that it just lives somewhere, doesn't get deployed. Most of the models never see the light of the day, and that's the sad reality of it. But what if we had a genie that we could use to build all these models and just take away all of this complexity that we have to face when we are building these models and deploying these models and doing all this machine learning operations work? Today, we heard from Anis and Carl beforehand about how to do these things on when you are using this with TensorFlow as a TFX, or you are doing this on a fully open source manner on using Kubeflow. TensorFlow TFX is also fully open source, but different ecosystems, and you can use these with different open source tools as well. But what if there was an easier way to do this? So enter Cloud.AutoML. Cloud.AutoML is a tool that is provided by Google on to use and build your custom machine learning models from your own data set. So how does it work? You have your own data set that you will use on Cloud.AutoML, which will store that data. It will train your data for you. It will deploy that model, and you can also use it to serve. And in the end, you can use it as a REST API, or you can just use it as a batch solution on Google Cloud. You can also export that model outside. So let's see how it actually works. So we know about our Vision AI, where okay, fantastic, awesome. So we know that Google Cloud provides APIs around Vision and other tools similar to that. But if I upload an X-ray image over there, the most of the information that it can give me are things like radiography, and there's a shoulder involved, which is fairly good actually. I did not expect it to give so many details around this. Like there's a joint involved, and this is medical imaging, it's a chest X-ray, details like that. But if I wanted to actually use this image to figure out whether there's pneumonia in this image or not, you can't really do that with the Vision API that is available out as a service from Google Cloud. But what you can do is you can use Cloud.AutoML to train and build your own custom machine learning model. And then once you have that custom machine learning model, you can deploy it and just use that model for your purposes. So for this example, what I have actually done is I have built this model which classifies the images between whether the X-ray has pneumonia in it or not. So what we will try to do is we will try to run this model onto a local machine. We built this model on TensorFlow.js, on AutoML, exported the model using TensorFlow.js. Now we're going to try to use it. So with this, running the model locally, everything is on local, no server calls are being made. And I just uploaded an image, and we will see the result here. This loading time is there because this is for the first time that I'm loading that model into the page. You can also reduce that time. I think Jason, the talk that is after me, Jason will talk more about that. So let's see. Oh, over here we see the probability of normal, that this is a normal image, is 0.61. This is 61% probability that it's not a pneumonia case. Let's try a pneumonia case over here. And now we see how quickly the computation happened, because this time the model was already loaded. And the probability of pneumonia is 94% on this image. This was the data that was not available on Vision AI. the solution that is available to you using an API. But what we did was we built our own API using our own data set. So how do you actually go about doing this? For this example, I used Kaggle had a challenge that was going on, and we used that Kaggle pneumonia data set. But for another example that I'm doing today, we will try to do something from the beginning. What we're trying to do is, we have seen a lot of examples about images. So I just wanted to do something that is non-image based. And for that, we have this IEEE data set, which talks about how do you figure out fraud in credit card transactions. So we have some credit card data information in here, 651 MB of data information. We have transactions in here, transaction amount in here. You can see how other people are trying to solve this problem. But what we can do is we can take a look at how we would do this with Cloud.ml. So for the first thing that we will do is we will go to our cloud dashboard. So we go to our Google Cloud Platform project. This is here we are. Now we will go to our AI section. So great thing to note, like all of the different AI tools are here. So right now we will go into tables, but you can also build custom models for natural language, for vision, for translation. I'm not sure if video intelligence is available, but you can do all of these things for your own data sets. So let's go into tables, because that is actually one of the most available data sets that people don't really use a lot. So over here, we have our data sets that we can use and build models upon. Today, we're going to take a look at the IEEE fraud detection. I have also done this talk beforehand, and every time I end up using a new database system. OK, so let's try with the IEEE fraud detection one. So let's go in there. I've already uploaded the dataset, but I'll just show you how exactly you can do that. So let's go to import section. Generally, I tend to tell people that always upload your data already onto Google Cloud Storage, and then just point the correct bucket location. So we are going into our AutoML bucket, and I'll choose the IEEE fraud detection, and I can just select the file from here. This will be much faster than uploading the files from your local. Even better, if you are already using BigQuery, just point it to the correct BigQuery table, and it will just import the data for you automatically. Then once you have imported your data, you can go take a look at some of the information about your models and your data that we imported. We saw this on TFX as well as Kubeflow, that these tools are available for everyone to use when you are doing an end-to-end pipeline. Here you can also take a look at that information. So we have information like all these different columns. Some are numeric types, some of categorical types. How many values are missing from there? How many values are invalid? How many distinct values are there? And once you assign a target column, so for this one, we are trying to, our target column is whether this transaction is fraud or not. You can see the correlation with the target as well. So sometimes you will see that some data has very high correlation. You might actually want to take a look at the data and ensure that that data is actually not nulled and like doesn't have missing values or something like that. This is also a really huge table. We have 394 columns in here, and this is 657 MBs of data. For tabular data, that's actually huge. OK, so we can take a look of this data. We can start doing some basic statistical analysis on this. On Kaggle, if you take a look at how generally people approach these problems, you will see that the first thing to do is understand your data. And this is a really great place to upload your data, and just very quickly you can see basic details about your data. And you can start getting sense of whether this data is actually usable or not. Then we go into training the model. So to train the model, it's as simple as giving the model a name. So let's, what I end up doing is generally I give it a name about for 3 hours. I'm going to train this model for 3 hours. The best part about this is you can just specify a number here on how much time do you want to train this model for. So for this model, we are going to train it for 3 hours. What you can also do is you can go up to 72 hours, and if your model is trained already and it can't find out better accuracy or whatever optimization objective you had, it can automatically stop itself early. Or you can disable it and it will take the whole time. But I generally end up enabling it because I don't want to spend 72 hours of budget time in there. If my model approaches best accuracy, or my best objective in 2 hours. I don't want to waste like next 70 hours just cause. Okay, at this point, you just start the model training. That's as simple as that. You have your model training started. What I did was I also started a training for actual 72 hours, and I did a training for 2 hours. This was yesterday. So while these models are getting trained, let's take a look what actually ends up happening when you train a model. We see some basic details right here, that area under curve is 0.56, or accuracy is 97%. That's really good accuracy. Let's see more details around this. So full evaluation. All right. So now we can evaluate our model. So not only we got the data, we trained the model. Now we are at the evaluation phase of our model. So we see that actually it's really good. We have 97% accuracy. Log loss is low. You can also set a good score threshold over here and see how it's performing at different score thresholds. So we can see like at 0.50, our F1 score is 0.49. You can also see the rate and confusion matrix over here. You can see how your model performed over time during the training process as well. You can also see the feature importance. This you can use and use for later to say, next time that I'm collecting data, I will try to ensure that these values are properly filled in and they're not missing any data values. Once you have all of this, then you can actually start using it right there. To test and use your model, you can use batch prediction. So the best way to do that would be to upload the data into BigQuery. You can also use CSVs from Google Cloud Storage. And the result can also go into BigQuery or to Google Cloud Storage. The thing that I like about it is you can do actually online prediction. So we just built a model which can figure out whether a transaction is fraud or not. I wouldn't want to run this at like midnight every day. I would rather run it every time a new transaction comes in. To do that, you can do an online prediction. Now, this here won't look great because we have 393 rows in here. So what you can go is a JSON model view. And you can see the payload of the request that we are making in here. These values are in the same manner that we defined our rows of data. You can pass in multiple values in here as well. Not as much known feature, like there's only one value that we are passing in here, one whole input. This is the complete input that we got from the user for the transaction, and we can predict with this. We are trying to predict whether it's fraud or not, and we see the confidence score is 0.99 of whether this is not a fraud. So at this point, we have the complete model, and it's available for us to actually use. We see that we just made a call over here. How would I actually make this call on server side to actually make it like from my API? So what you can do is you can go to this page. Hopefully it opens up quickly. All right. So right here, we have a Node.js example. You can do Java or Python, whichever one you are more familiar with. And it's fairly simple. You set up your project and your model path, your project ID and region, things like that, and just make the call. It's a simple predict call, which takes a payload value in and returns you the results. And you can just take all the results and return the response back. This whole code will give you the complete API that you need for your users. So at this point, like this is a pretty good model, and we can start using it. But why would I actually want to use Cloud AutoML? So let's take a look at that. Right. So why would you actually want to use as a Cloud AutoML? We talked about like some problems that we have as users where the data is messy, or we see that there's a lot of problems around computation, model jobs break, and things like that. Why would you want to use a Cloud AutoML? We, as humans, like there isn't a lot of talent that is available around machine learning. We see a lot of people, a lot of hype going on around it. But when you actually look for talent around machine learning, it's fairly hard to find those people and actually to hire them. Let's say you actually hired a person and you are now using their skills to actually build a machine learning model. It still takes a lot of time, not only in data pre-processing, cleaning, it's also setting up those pipelines, running these experiments, coming up with the best model architecture, trying to find out various hyperparameters, trying to tune them, and running all these experiments, keeping track of all those things still takes time. And moreover, as soon as you add the human cost as well as the time cost, the cost is actually high for something that you might not even end up using. So with AutoML, what ends up happening is you can use all these things. You can start using your data right away, the model for your data. One of the good things that I might have skipped over here is, let's go back to this. On training part, oh, that was right here. So let's go back to the model section. So the training will take several hours. It also includes the time to set up the infrastructure and tear down. So even this time, you are not getting charged for that. And when we consider that time into how much effort that goes into setting up the infrastructure, tearing down the infrastructure, and all these extra costs that go around building your product, it's a lot of cost, and you actually want to reduce as much as possible. So I suggest people to use as much as possible for Cloud AutoML. Okay, but what if I actually built the model, I like the model, I actually using it, but what if I actually need even more flexibility? And I've tried multiple data variations, but I'm not getting that on Google Cloud AutoML. Highly unlikely, but if you are not, you can go to TensorFlow Hub. At TensorFlow Hub is a repository where you can browse different machine learning models for your own use cases. And these models are trained models, which you can also retrain for your usage. And you can try it on different formats as well. So let's take a look at some types of models here. So if I go into image as a class, I can get image classification models in here. I can get landmark models. These are like pre-trained models. This is a collection, but there are also pre-trained models that are available in here. So let's go take a look at, there's Big GAN here from DeepMind. You can also filter for models that you're only working for TensorFlow JS, and I don't see any in here. Okay, let's go back to TensorFlow Hub, and then we will filter for TFJS only models. So you will see these models that you can use directly using TensorFlow JS in your browser. And I think Jason will talk more about these things, these models in here. You can also get models which work for TF Lite, which will be your Android or iOS devices. And these, I think, also work on Raspberry Pis. You can also get Coral devices and run your models on that. You can get these different models from here. The best part that I actually like about this is, let's go to one of the examples. Let's go to BERT. I really like, so in here, these Colab tutorials. Not only you can use an existing model, you can also learn about how can you use that model, how is that model built, and how to fine tune that model. So here, this is Colab. It's totally free to use. We have all the code in here on importing the model. So here we import the whole model, the pre-trained BERT encoder, and then we get our data set. Right here, we are using TensorFlow's data set, but you can load your own data set in here. We tokenize the data. We do all the pre-processing that we need to do, and then put the whole thing together to build the model. And you build the model, you can run it. And to run this whole thing, you can just it's a simple Jupyter notebook. And you can run this whole thing and learn more about this as well, and totally for free. And of course, there's Colby's in here. Nice. Okay, so that's TF Hub for you. But what if you are actually working inside a team, and things that you can do on Colab, you can actually share those with different people in your team, and everybody can collaborate on those repositories. But as you grow and become bigger and larger teams, you end up having trouble with not only the model file that you are using to write code in, but also the assets around models. So for that, Google Cloud provides Cloud AI Hub, which is a central place where you can come in and you can have different types of assets in here. So we talked about Kubeflow Pipeline today. Let's go to the demo of this. AI Hub. Awesome. So here we have AI Hub, which has different types of assets that you can share between your team. Now, this is my personal one. I don't have any assets shared here, but you can share those assets. You can start those assets to see, have a quick way to go to those assets. Nothing in here. The page does a full reload. That's not great. Let's wait. Okay, I just want to show more about these. So you have different categories of assets that you can share. There's, of course, the data that you can share between your team. There's, of course, some data that is available from Google Cloud. I think most of this data is available also on dataset search. But you can also take a look at here, like one of the recent cases happening around COVID, and the data set is available over here as well. You can search for those data sets and look at different types of data sets. Of course, the Kubeflow pipelines that Carl mentioned today, you can have one of the existing Kubeflow pipelines. Like if you wanted to run, let's say, right here, a time series model, which works really great on if you're doing any kinds of advertisement or advertisement type of work. And you can do a time series analysis using LSTM and TensorFlow and Cloud ML Engine. This is a complete end-to-end solution over here. You can do a OCR character recognition over here. Similarly, like there are more available Kubeflow pipelines. These are end-to-end systems that are already built that you can directly use into your projects. Of course, ML containers, notebooks, services, like all of these things are available here. Trained models as well. I don't see any trained models over here because I think all of those are available on TF Hub now. But if my team built a trained model over here, you can put that here as well. So data and your model assets will come in here from your team as well. All right. The best part about this that I really love is technical guides. Again, same as TF Hub. It's great to use something that is available, but it's even better if you can learn from it. There are, like, I really love this article where you can just use serverless machine learning, how to build serverless machine learning model on Google Cloud. And they talk about using vision APIs and Cloud Video Intelligence API. And it's a complete blog post here. And like with all the details around how do you want to use it. Similarly, you can filter by different types. And this is a really great hub as a central place that you can come in for all of your machine learning needs around when you're working with a team. So how do I actually go about, what would you do if you were doing a new project on machine learning? The best use case that I generally tell people, the best way to get started is start looking at the Vision AI or the already available APIs that are available from Google Cloud. You might find your answer right there. Like I was not expecting here for Vision API to actually return that this is an X-ray image or that it contains chest in here and there's a neck in here. And you'd be surprised at what this can do. Like sometimes people tell me they want to get a character from the image, and like right here we see there aren't a lot of characters in here, but there's R in here, and you can get that from here as well. Different properties, different safe search, whether this is a medical image or not, whether this is a violence in this image or not. And you can do most of these generic use cases from here on the API. If those don't work, try going to Cloud Auto ML. As we talked about that, like I actually wanted to figure out whether there's a pneumonia in this image or not, how good are this person's lungs functioning. And you can go to Cloud Auto ML and build your own model over there. And even then, at this point, if you're not satisfied and you still need more hands-on work, like both of these systems are totally out of your control. You can't really do a lot of those things around hyperparameter tuning and anything around that other than your data. You don't really have a lot of control over anything. On API side, you don't really have any control. On Cloud Auto ML, you have most of the control over data and how much time you want to spend, but you don't really have any other control. If you really want a lot of control around how you build your models, how you deploy them, you're trying to cut down your costs and details like that, you can always go to TensorFlow Hub and AI Hub and build from there. The way I generally approach, most of my problems are generally not solvable by Vision API. So I actually start with Cloud Auto ML. It's a really great place to get a quick feel about not only your data, but also what kind of models you can build, what kind of models architectures even would work. And if nothing else, it would actually give you at least a baseline about what kind of models and what kind of predictions you can expect from your data. It's a very easy way to filter out projects that you don't want to work upon. Let's say a client gives you a 10 MB of file and tries to ask you to like build a machine learning model on it, and like the data is not really useful. You can't really do anything on that. So with Cloud Auto ML, you can very easily run a quick search and like run a quick project on that and get a peace of mind that you didn't spend like days trying to build a pipeline and things like that when there was no actual value in doing any of that. So once things pass through my baseline criteria that we can actually, this data is actually useful and we can build something useful out of it, then I actually start looking into TensorFlow Hub, Kaggle, AI Hub, or anything that is available, any literature that is available around building these different models, any already available asset, that'd be great. Already available model, fantastic. But generally, it's not available. So either we end up retraining those state-of-the-art models that are available on TensorFlow Hub, or you end up finding a really innovative way on Kaggle by some of the winners from previous competitions, or you end up going to AI Hub and realize that some of your teammates might actually have built something like this already, and you can just fork from that and start working on top of that. And finally, once the model is ready, I really like to use my models available as quickly as possible. So they generally end up taking the point of becoming a REST API, but I really love it when I can export them out as a TensorFlow.js models and use them directly into my browser. That's my ideal workflow, and I really enjoy those kind of things. So that's actually it. If you have any questions or compliments, I'm here. Thank you, everybody.
Awesome. Thanks, Vikram. That was a lot of information in a short period of time. I think you did a great job. AutoML is really, really awesome. And, you know, Kaggle recently used AutoML to build a spam filter instead of, there's an article about it that came out recently. I guess you mentioned cost as one factor in why you might go with AutoML and begin using that. And you kind of went over a lot of different points. Are there some main reasons besides cost why you kind of go for AutoML versus kind of building a model from the ground up?
Not really. As I talked about, like the talent around machine learning is fairly scarce, and like even though you might find a great machine learning engineer, they might be domain specific. There are engineers who only work on image data. The engineers who only work on text data. And today, you as a company might be working on text-heavy computation. But if you are a startup like us, like that might change in 6 months from now. And you might need to again find and hire a new person, bring them on board through all these processes, and on a different type of problem. And as maybe this is coming more from my startup background experiences, things change rapidly in a startup enterprise. And what you want to do is you want to have quick way to try these things out. So not only time and cost itself, both of those are very valid concerns, but hiring itself, no matter how good of a person you have on your one team, they can't be expert in everything. And with Cloud AutoML, you get the flexibility of using tools that are already available out there.
Definitely, yeah. I think that transfer learning, framework is something that's saving a lot of time, and sometimes I find that perhaps ego becomes something that plays a part in that, being that, you know, people want to build it themselves. They don't want to use something else. But
yeah,
when you're talking about like an enterprise situation, you know, and you need to get something done for a client, you know, I'm in the same boat as you, where I work, you know, at a startup, and we just need to get things done, you know. And so I think it's really awesome that this is available, and appreciate you sharing your insights about it. It's super cool.
Awesome, of course.
Yeah, awesome. I think we're ready for our next talk. Thanks, Vikram.
Awesome, thank you.
Hi there. 1 second, I'm just going to share my screen. All right. So hopefully everyone can see my screen. Nice to meet you all today. My name's Jason Mays. I am the developer advocate for TensorFlow.js here at Google. And today I'm going to be talking to you about machine learning in the browser and beyond in JavaScript, essentially. And before I get started, I just want to give a quick overview about my background. I'm actually from the web engineering background. And you might be wondering, why isn't web engineer here at a machine learning kind of session? And essentially, over the years, I ended up working my way combining JavaScript with machine learning, and that is why I'm here to talk to you about that today. If there's one thing you take away from this slide, I spent 16 years playing with JavaScript. And for that reason, I've got a few things to say about that in terms of why it's actually interesting to consider for a use case in machine learning. And on that subject, the first thing to talk about is that we can actually use JavaScript to run in pretty much any location. JavaScript can run in the browser, on the server side, desktop, mobile, and even Internet of Things. And if we dive into each one of those areas, you can see many of the technologies you might be familiar with already. All the popular web browsers there on the left-hand side, We've got Node.js for server-side, React Native for native applications on mobile, Electron for desktop native applications, and even Raspberry Pi via Node.js over there for Internet of Things. And JavaScript is like the only language that can run in all of these environments without additional add-ons and plugins and all this kind of stuff. So for that reason alone, it's very powerful. However, with TensorFlow.js, you can retrain by transfer learning, or you can write your own machine learning models completely from scratch if you so desire, just like you can do currently in Python. And of course, that means you can dream up anything you may wish, from augmented reality, sound recognition, sentiment analysis, and much, much more, which we'll see of today. Now, the first way you can use TensorFlow.js is three different ways, depending on your background and experience with both machine learning and JavaScript. The first one I want to talk about are the pre-trained models. These are really easy to use JavaScript classes that even if you have very limited knowledge of machine learning, you can actually use these very quickly and effectively. And we've got many of these that are available to use out of the box, fully open sourced, such as object detection, body segmentation, pose estimation, and all the other things you may be familiar with here. Even BERT has been converted to run in the browser, and that's pretty cool. So let's dive into some of these models and how we can actually code them to use them in the web browser and beyond. So the first thing we're going to look at is object recognition. This is actually using Cocoa SSD behind the scenes and has been pre-trained on 90 object classes. And as you can see, I've made a little demo here on the right that allows me to get the bounding box information back and render it to the browser to highlight the objects in the scene. And we display the class and the confidence values there as shown. So let's walk through the code on how I created this so we can see how this is actually put together. So first up, we've got the HTML. Nothing too fancy here, just bread and butter HTML. First thing we're going to do is import some style sheets. Second, we're going to have a section for our demos. And initially, this is going to be invisible because we want to wait for the machine learning model to load. And then when the machine learning model is ready, we'll then make the demos visible so you can then click on them and interact with them. Now, within this section, we're going to have a bunch of images that you can click on. And when you click on them, you're going to get the results for the object in that image. And these are contained within a div element so that we can actually render other things to that area later on, as you'll see. And then all we need to do is import some JavaScript libraries. The first one is TensorFlow.js itself. The second one is the Cocoa SSD model that we want to use, which is one of our pre-made models that I just spoke about. And then the third thing is the script, the actual JavaScript we're going to write to use both of these things. So that's all you need for the HTML. So let's dive into the JavaScript, the script.js on this page. So the first thing we're going to do is we're going to grab a reference to the demo section in that HTML, and that's simply using getElementById, so bread and butter DOM manipulation. And we're then going to have a global variable called model, which is just going to be undefined for the time being until we've loaded. So the next thing we need to do, of course, is load the model. Now, because we imported Cocoa SSD with our script tag on the previous slides, this Cocoa SSD variable will now be available to us. And we simply call Cocoa SSD.load. And because this is an asynchronous operation, we use the then keyword. So when it's ready, it will then call a function of our choosing and pass us the loaded model. This loaded model we can now assign to our global variable model, so we know that the model is loaded and we can use it in our other code. And we can then remove this invisible class in the CSS such that the demos now render correctly. So you'll see in the demo later on, it goes from a grayed out state into a nice colorful state, so you can actually know when to click on things. Next, we're going to get all the images that we want to be clickable. And of course, I gave them a class of classify on click in the HTML. So I'm just going to grab all the elements that have that class. So we're going to get an array of images here called image containers. And we're going to iterate through all of those image containers. And essentially, we're going to get the child image node and add an event listener for a click event and associate a function called handle click when that element is clicked. So if we go into the handle click function, you can see all this does here is when it executes, an event is passed. And if the model has not already loaded, because it does take a couple of seconds, then we're just going to return straight away, just in case someone tried to click on something before we are ready. Otherwise, we're going to go ahead and call the model.detect function. And this, of course, takes an image-like object as its parameter. In this case, we're passing the event target, which is the image that was clicked. And again, this is an asynchronous operation, so we wait for that to finish, and then it will pass the predictions to a function of our choosing. In this case, I've named it handle predictions. So let's dive into the handle predictions function. And essentially, you can see here, we just get a JSON object passed back, which you can just console.log if you wanted to see what it looks like. But essentially, it's just an array of objects for things that we think we found in the image, along with their confidence values and so on and so forth. And essentially, we can then iterate through those objects as such using a for loop. And we can start creating some new HTML elements so that we can start rendering out the details to the screen. So all I'm doing here is I'm creating a paragraph tag, and I'm setting the text of this paragraph tag to contain the class and the rounded score for the accuracy, essentially. I then simply add some style to this paragraph so it appears at the bottom left of the image. And then I simply add a div element so I can actually have a bounding box. And this div element is just going to be lots of dashed lines so we can have the bounding box showing nicely. And I'm just going to put this at the position at which the ML classification recognized the object. So I'm just setting the width, height, top, and left. And with that, we've got a bounding box. So all I need to do now is add these two elements I've created in memory to the actual DOM, the actual the web page itself, and we're basically good to go. So finally, there's some CSS. This is up to you how you want to style things, of course. But here I've got some nice transitions, and I've got some like borders that are dashed and so on and so forth, just to make it look pretty. And if we go over to the live demo, you can see what this is going to look like. So I'm going to stop sharing this screen and go over to my other window. One moment. Share screen again. And hopefully I can now find my other tab. Here we go. Good stuff. So now we can see, essentially, if we switch to my new window, I think I still see myself. Perfect. Yeah. You can see here that this is the demo running live in my browser right now. And if I click on any of these images, you can see we get the instant classification of the objects it can detect in the scene. And notice here, even though we've got multiple objects, they all come back nicely, and the objects are different types and so on and so forth. So now you can see how you could use this very easily to detect if your dog at home is trying to eat your treats or something like this. It would not be too hard to take something like this and turn it into a smart cam. Now, what's even better here is that if I enable my actual webcam right now, you can see me in my bedroom talking to you all, and we can do this with webcam imagery as well. So if we just call the predict function many times per second, we can actually get a live update of everything, as you see here. And notice how fast this actually is as well. This is running in JavaScript in the web browser and at very high frames per second. So JavaScript is very, very good at the display of information and computer graphics and all this kind of stuff. And that's basically what it's been designed for. So it's very easy to make these visual kind of feedback systems, as you see here. So I'm now going to stop presenting this and go back to the slides. One moment. Share screen again. And boom, there we go. Back to the slides. If you can present my slides again for me. So next up, we have face mesh. This is just 3 megabytes in size. And essentially, it allows you to recognize 468 facial landmarks. So this is just another pre-made model, like the one you saw before, but this one is aimed around identifying parts of the face. And you can see here, this can be used for many interesting things, including augmented reality, such as the image on the right-hand side there. This is actually by Modiface, which is part of the L'Oreal group. And this lady on the right is actually not wearing any lipstick. We're actually using face mesh to understand where her lips are, and then using WebGL shaders to then overlay 3D graphics on her face, so it looks like it's actually on her face and looking very realistic. And she can change the shades of a lipstick and so on and so forth. And this is really great in today's world where everyone's stuck at home, they can't go touch the products, and maybe you don't want to try on products that other people have touched. So in that case, this is very useful and can help you still shop in these times. And I just want to flip to the demo for this as well to show you it running live, because it is really cool. So if I just go ahead and swap my screens again, there's going to be a bit of screen swapping going on today. One moment, share this. So now you can see that I'm actually doing this live in the web browser. And if you can present my screen again, whoever's moderating. Can someone present my screen? Thank you. Perfect. So here you can see my face is being detected in real time on the left-hand side here. So the machine learning is going on the left. But because this is JavaScript, there's very rich libraries for 3D graphics, as I mentioned before. So on the right-hand side here, you can see I'm rendering a 3D point cloud of my face in real time at the same time as doing all the machine learning, all in real time in the browser. And you can see here I'm getting like 25 frames per second, even though I'm live streaming to you right now, which is using up my processor quite a bit. But this is running on the CPU. You can see at the top here, This is running in WebAssembly, WASM, and that means it's executing on the CPU of the device in the web browser. I can actually switch this to WebGL, and then I could actually get even faster performance by leveraging the graphics card of the device. And if I do that when I'm not streaming, I can get like 45, 50 frames per second for this particular model, which is pretty cool. So things run really fast, it's super lightweight, and allows you to do whatever you might want to dream up. So I encourage people to kind of get creative with these models and figure out how they might want to apply them for their use cases. Okay, so I'm going to stop this and go back to the slides again in one moment, sharing my screen. Boom, okay, back to the slides. So here, next up, we have body segmentation. This allows you to distinguish 24 body areas across multiple bodies in real time. This is called our body pix model. And you can see here on the right-hand side how this works in action. And you can see like multiple bodies being detected at the same time, and all the different colors represent different parts of the body. And even better, we can get an estimate of the pose as well. But that's the blue lines you see in the image on the right-hand side. Now, with a bit of creativity, we can actually emulate many of the superpowers we've been promised in the movies by now. And I just want to share a few examples that I've created to illustrate this. The first one is invisibility. This is running live in the web browser, and I made this in just one day. And I'm able to remove myself in real time from the webcam in the browser. But notice as I get on the bed, how the bed still deforms. So this is not some cheap trick where I'm just replacing the background with a static image. This background is being updated in real time, and I'm only removing the body pixels, and I'm calculating what the background is over time. So this can lead to some cool effects. But what about lasers? Once again, if you're talking about WebGL, we can have people from our community making things like this, which allows him to use WebGL shaders to understand how to combine this with face mesh to shoot lasers from his mouth and eyes, just like you can in Iron Man or something like this. And I thought, well, this is pretty cool, but let's go one step further. And some of you may have seen recently on social media, I created this kind of teleportation demo that allows me to segment myself in real time. I then transmit myself using WebRTC, web real-time communication, over the internet to some remote location, and then using WebXR, which is web mixed reality, essentially, I can then place myself in a remote room, and the person who's watching me in that remote room can walk up to me, they can hear me from the right angle, and they can move around me, and so on and so forth. So now, instead of having a video conference where you're stuck in a rectangular box, you can actually be physically present almost in 3D, and it adds to the immersive feeling and more personal feeling of meeting someone, especially in the times when we're stuck at home and it's very hard to be out in large groups and so on and so forth. And of course, other delightful creations can be made beyond this as well. And here's another one I created for clothing size estimation. I don't know about you, but I'm terrible at knowing what clothing size I am out in the wild. I always forget my sizes. And of course, body shape changes over time as well. So here, in under 15 seconds, I can use body pics to figure out what my size is, giving my measurements for chest and height. So no, not the height. Using my height, I can figure out my chest and my inner leg and waist and those measurements, which allows me to then select automatically on the web page if I'm a small, medium, or large, that kind of stuff. So now I can buy stuff without having to return it all the time and save time and money because of that. And of course, we've seen the community also do some great things too. And this guy from Paris in France, from our community, has managed to combine it also with WebXR and WebGL, so that he can scan any magazine and bring that person from the magazine into his living room. So maybe you're interested in fashion or something like this, and you can now go and inspect those clothing in more detail in a way that is more meaningful to you. And notice he's using his mobile phone here. He's actually using a 2.5-year-old Android device to do this. So it doesn't require the latest hardware to do this, but it's all running in the web browser on that device, which is pretty cool. Now, the second way you might want to use JavaScript-based machine learning is transfer learning. Once you outgrow our pre-made models, maybe they don't quite work with the data that you have available to you, you might want to retrain those models to work with data that's more meaningful to you. And of course, if you are a machine learning expert, which I'm sure many of you are given the audience today, you can do the same stuff you do in Python, then you can do this all by code if you wish. However, today I want to focus on two examples that allow you to do it much faster than that for more simpler use cases. And the first one, of course, is Teachable Machine. Now, this is great for prototyping because it allows you to do everything in the web browser. At no point other than delivering the web page is a server used. We're going to do the training in the web browser, and we're going to do the inference in the web browser. So the best way to explain this is to go and use it. So let's switch my screen and show you how this works. So once again, I'm going to stop my presentation here and flip over to Teachable Machine. Boom, there we go. So when you go to teachablemachine.withgoogle.com, you are presented with a page something like this. Right now, Teachable Machine can allow you to train to recognize images, audio, or specific poses. And these three are just the starting points. I'm sure more will be coming soon, as it says here. But for today, we're going to go with image. So you click on image, and by default, you have 2 classes, but you can add more classes if you like at the bottom left here. Now I'm going to go ahead and name these so they're more meaningful. So the first thing I'm going to recognize is myself. And the second thing I'm going to recognize is a deck of playing cards that I've got in my room right now. So all we need to do is click on webcam and allow access to our webcam, and you get a live preview of what's coming from the camera here. And we can use this to take samples of the object you're interested in. So I'm just going to sit here and move my head around and get a few samples. So one moment. There we go. Maybe a few more. There we go, cool. So we've got like 38 images of my face in various positions. And of course, if you're doing this more properly, you'd do this with more variety and have more training data. But for the purpose of today's demo, that's all we need. And then for class 2, we're going to do exactly the same thing. I'm going to hold up this deck of cards instead. So I'm going to get roughly the same number of images, so about 38. Okay, 41, that's close enough. And then I'm simply going to click Train Model. Now what's going to happen here is that the TensorFlow JS is going to retrain the top layer of this model that Teachable Machine is using, which is actually a KNN classifier built upon MobileNet. And we can then repurpose the other understandings that MobileNet has already learned to then classify these objects here. And you can see in under 15 seconds, it's already trained, we're done. And we can see on the right-hand side here, a live preview of it in action. And you can see here that it predicts the output as JSON, which is correct. That is currently what's showing on the live preview. And if I hold up my deck of cards, you can see it goes to cards straight away. JSON, cards, JSON, cards. And look how fast that was. In under 2 minutes, we've managed to make something that you could use for a prototype to demonstrate something, and you're good to go. So if this is good enough for your needs, you can simply click on Export Model here. You can click on Download, and you can download the various files that are containing the model weights and such. And you can host those on your web server or CDN, and then use that on any website you like using the code below. So really not too hard at all. And of course, if you're trying to make more robust models, you would need more training data to avoid any biases and so on and so forth. And for that, as already mentioned, Google Cloud AutoML is super for those kinds of situations. So if I stop presenting this and go back to the slides, share screen. Boom. So the next thing is Cloud AutoML. And of course, the previous presenter has already gone in this in much detail. So I'm just going to give a very high-level overview here. But essentially, as already mentioned, Cloud AutoML allows you to train custom models in the cloud. However, it can export to TensorFlow JS, which is pretty nice too. That's why I just like to touch on this very quickly. You can see here how someone's trying to recognize different flowers. They just uploaded all their folders of flowers to cloud storage, and then you can import that via Cloud AutoML, as you saw before. You then set your various options if you want to have a higher accuracy or faster predictions, and set your various hyperparameters if you want to. And then you click on continue and wait for it to train, as you just saw. You then have an option to download for TensorFlow JS at the end there. You download that zip bundle and you unzip it onto your server and store it somewhere on a CDN. And basically, you can then use those files on your own website. And you might be wondering, well, how hard is it to use TensorFlow JS trained from Cloud AutoML? In fact, it's so easy. It fits on just one slide, even easier than the demo I showed you before. And let me just quickly walk you through this. All we need to do is import 2 libraries at the top in HTML. So this is just the TensorFlow JS library and the Cloud AutoML library. The third line here is just a new image that I want to classify, which is just an image of a daisy that I grabbed from the internet. This could be anything. This could be the webcam. It could be something else if you wanted to. But for today's demonstration, I'm just going to use this image here. And then this is the actual JavaScript, just 3 lines of code. All we need to do is wait for the model to load. So tf.automl.load image classification. And this is just past the model.json file that you would have downloaded from the previous step and hosted on your website somewhere. So you just tell it where that is, and you await for that to load. And you use the await keyword because this is asynchronous. It takes some time to do so. And when it's ready, it will then be assigned to this model constant on the left here. We then grab a reference to our Daisy image, which is just above. I'm just doing a get element by ID, and you can see I've got the ID of Daisy up here, and now that's stored as constant image. And then all we need to do is call model.classify with the image we want to classify and await the results to come back. And again, this is an asynchronous operation, so this might take a couple of milliseconds, and then you get the predictions as a JSON object, which you can then iterate through just like before and print out or do something useful. So super easy to use, but this can be used for production level quality applications because you can upload gigabytes of data to Cloud AutoML, and the models there are very robust for the purposes of image classification and much, much more. And then the third way to use TensorFlow.js, of course, is to write your own code completely from scratch. And for those of you who are used to doing that, I'm not going to go into that right now because that's beyond a 40-minute talk. However, I'm going to concentrate on the superpowers and performance benefits you can get by considering using JavaScript over maybe Python or something like this. And essentially, to understand this better, we need to talk about how TensorFlow.js has actually been architected. Essentially, we have two APIs. The first one is a high-level API called the layers API. This is basically similar to Keras if you're familiar with Python. And in fact, if you've used Keras in the past, you'll be very familiar with our layers API. We even have the same function definitions and so on and so forth. The only difference is that you're using JavaScript over Python, but the function calls will be pretty much the same. Down below, we have the ops API, which is the more mathematical API that allows you to do all the linear algebra and that kind of fun stuff. So if you do want to get down and dirty of the code on the lower level to make your own models or new things from scratch, you can do that with our ops API as well, just like the original TensorFlow. So bringing this all together, you can see how our pre-made models at the top there are sitting on top of the layers API. The layers API sits on top of the core or ops API, depending what you want to call it. And this can then talk to different environments, such as the client side. Now, on the client side, I'm referring to things like the web browser, WeChat, React Native, those kinds of environments. And each one of those environments understands how to talk to different backends. And by backends, I simply mean hardware device. So the CPU, the processor, WebGL allows you to run on the graphics card in JavaScript in the web browser. And WASM, or WebAssembly, is how we get better performance on the CPU. So depending what's available to you, depending what device you're running on, you can choose which one of these you want to execute on. However, CPU will always be there, but it's the slowest form of execution, and you probably want to be using WebGL or WASM for real-world usage, and most devices actually support this. I think WASM has over 95% support across devices, and WebGL is like 86 or something like this. So very widespread support, and that can run on an NVIDIA graphics card or an AMD graphics card. So that's already pretty cool that you can run on many more devices. Now, the flip side of this story is that we've got the Node.js story, and this is for server-side stuff. Just like you would be doing Python already in the server-side, Node.js is our equivalent for that in JavaScript land. And the Node.js actually talks to the same TF CPU and TF GPU backend that's written, I believe, in C++ or something like this. And that means it has the same performance as Python for model inference because we can also leverage the same CUDA acceleration and AVX support and so on and so forth behind the scenes as both Python and JavaScript are basically talking to the same backend, which is written in C++. So with that, if you are doing all your ML development in Python, there are some ways you can have a more easier journey to the web via Node. So you can actually take a Keras model that you've saved and load it via our layers API in Node.js if you want to take something from Python land. Or the equivalent on the lower level is to take the TensorFlow saved model, and you also load that in Node.js without any conversion and use it on the server-side environment in Node.js for free. And there's some advantage to doing that, as we'll see in just a second. Now, the third thing you might want to do is convert a TensorFlow saved model from Python and use it in the web browser. Maybe you want to reach more people and get more people to try it out or something like this. As a researcher, that could be useful to you. With the TFJS converter, you can basically do that. And there are some caveats with that. We don't have all the ops support that TensorFlow Core has right now. Obviously, we're playing catch up. We're a newer team. We're only 2 or 3 years old. TensorFlow Core has been around for much longer. So we are open source, and we welcome contributions to those ops supports if you want to add more ops on the TensorFlow.js side as well. But honestly, a lot of models do convert without any issues. It's only if you're using some more exotic operators that you'll find that is an issue. And of course, it will mention which operation is not supported. And you can either choose to implement that or use a different op to get around that. Cool. So let's talk about performance then. This is for MobileNet v2, and you can see that running on the graphics card in Python, it takes 7.98 milliseconds, and running on a graphics card in Node.js is 8.81. So it's within the margin of error pretty much, depending which way the wind was blowing on the server on the day that we recorded this result, and it's pretty much the same. But the real beauty comes when you're doing a lot of pre and post processing. Now, often, as you're probably aware, in machine learning, you have to manipulate the data coming from sensors or so on and so forth to get it into a format that the machine learning model can digest. And this can be very non-trivial at times. So in JavaScript, if you do the pre and post processing in Node.js, you can benefit from the just-in-time compiler that JavaScript has, because we compile at runtime. And that can actually lead to a 2 times performance boost. As you can see here, for Hugging Face, the DistillBERT model, they converted to use Node.js, and whilst the inference was the same, the whole pipeline was 2 times faster because of that pre and post processing having been converted to Node.js as well. So, go play with some things. I do encourage maybe doing your models in Python as you're used to, but go play with it, putting it in Node.js for the pre and post processing. And then not only do you get the reach and scale of the web, but you also get some of these performance boosts for free as well. So it could be a nice marriage of technologies right there. So let's talk about some of those superpowers then. If we just focus on the client side for a second, so this is TensorFlow.js in the web browser, then we get the following kind of very useful benefits that are hard or impossible to achieve in a server-side environment. Now, the first one is privacy. If you're executing entirely in the web browser, that means any data coming from the sensors stays on the client's machine. At no point is the imagery or sound or whatever other data you're grabbing is never sent to a third-party server. And in today's world where privacy is top of mind, that's really important, especially if you're making some kind of healthcare application, as we saw before, or even something legal requirements. Maybe you're in Europe with GDPR rules and this kind of stuff. There's many reasons you want to execute things on the client side. Now, if you're executing on the client side, that leads to point number 2, lower latency. Because there's no round trip time to the server and back again, especially on mobile devices, the latency involved there could be quite high. You could be looking at 100 milliseconds or more just to talk to the server and get a result. That means you can have higher frames per second if you're classifying stuff in real time directly at the source where the sensors are, and the web browser has direct access to all of those sensors. Third point, lower cost. If you're not running a server, then of course you don't need to keep a server running all the time to do the inference, which means no hiring of beefy GPUs and CPUs and lots of RAM running 24/7. And if you're having tens of thousands of users per month, that can lead to some serious cost savings, maybe tens of thousands of dollars per month if you have a popular site. Fourth point, interactivity. As I mentioned before, JavaScript has been from day one all about being the kind of sharing of information and graphics and all this kind of stuff. And it's only got better since then. So we have very mature libraries for 3D graphics, charting, data visualization. And I encourage you to check some of those libraries out, as they're much easier to use than other things I've tried in other languages. And then fifth point, reach and scale. Anyone in the world can click on a web link and get access to the web page. That means you get the machine learning for free. It just works out of the box. Now, the same is not true if you're trying to do this over on the server side in TensorFlow Pipeline or something, because first of all, you need to install Linux. Secondly, you need to go install TensorFlow. Then you have to install the CUDA drivers, which is often quite tricky to do. Then you have to go and clone the GitHub repository. And then you have to read the README of the GitHub repository to understand how to use the code. And if all of that works out well for you, then maybe, just maybe, you'll be able to use that and get it running. So as you can see, it's a much higher barrier to entry going down the other path, as an end user at least. So this, if you're a researcher, could give you many more eyes on your cutting edge research. If you can provide your model to be executed in the browser, you can maybe have tens of thousands of people using your model to give you feedback and find any bugs or biases, which you can then fix faster than if just a few people from your team are only the ones using it. And of course, on that note of reach and scale, we mentioned on the GPU, we can support 84% of devices via WebGL. And that means we can run on a MacBook Pro with an AMD graphics card. And I believe TensorFlow on the server side can only support NVIDIA, to the best of my knowledge, using the CUDA drivers. So we don't care what graphics card you have. As long as it can run WebGL, we're good to go. So the flip side of this is that on the server side, there's also some benefits here. This applies both to Node.js and Python, whichever one you're using here. So here you can see that you can use the TensorFlow saved model without conversion. And this is great if you're trying to integrate with a web team, as I mentioned before. A lot of web developers out there probably are more familiar with Node.js. And if you're working in Python for machine learning, this is a really nice way to collaborate with other teams. Second point, you can run larger models run on the client side. Often you'll be limited by the graphics memory of the client's device as to what size model you can load and execute on that device. Now, in most cases, it's not too much of a problem because many of the models are just megabytes in size. But if you were trying to push down a larger model down the pipeline, then it's probably better to run it on the client side, sorry, on the server side. And in that case, you can do that using Node.js. Third point, it allows you to code in one language. Now, if you're already using JavaScript, and currently 67% of developers out there use JavaScript as their kind of production language, according to the Stack Overflow survey of 2020, then that means you need to hire less people and you can reuse your code and so on and so forth. So just make maintainability just a little bit easier. And then the fourth point, Node has a very large NPM ecosystem. So just like the JavaScript on the client side, there's many libraries you can now use for doing many different things. And then the fifth point we touched on already is the performance. You get the just-in-time compiler boost that you don't get in other languages, which means you can get up to a 2x performance boost for your machine learning models for the pre and post-processing. So with that, I'm going to end with some resources. If there's one slide you want to bookmark or screen grab today and share with your friends, is this one here. Essentially, first up, we've got our website, tensorflow.org/js. Go there to learn all the basics about TensorFlow.js and a good introduction. Second point, our models are available on /models there. And I've just spoken about 2 or 3 models today. There's actually many, many more that we've open sourced and you can use right out of the box. And I encourage you to go play with them after the show. We are completely open source, just like the original TensorFlow. So if you are willing to contribute, check out our GitHub code. And there's much more README files there as well for more information on the various models and so on and so forth too. If you have more technical questions, we have a Google group that you can join. This is public, and our team tries to monitor this as much as possible. And then we've also got CodePen and glitch examples that are super easy to fork and use. And what these are examples showing how to use some of our more popular pre-made models with the webcam, with images and other data. So you can just fork that and have a starting point that works. And then you can just hack it and change it to do what you need very, very quickly. If you're looking for a recommended reading, I'd recommend the Deep Learning with JavaScript book. You can see that here from Manning Productions. And if you use Made with TFJS discount code, you can actually get 30% off that book and any book, I think, on Manning, in fact. So a great code to use for Manning. And then if you're interested, please come join the community. We do have this hashtag Made with TFJS. If you search for this on Twitter or LinkedIn, you can see even more projects that people around the world are making, not just myself and my team, but people around the world just like you who are starting out with JavaScript or new to machine learning or both. And they're still able to make some really great things. So do check out for inspiration. On the note of inspiration, I just want to leave you with one more. This guy from Tokyo, Japan, has actually managed to make a hip hop video using TensorFlow.js. And the key thing here is that he's actually just a dancer, but he's managed to leverage TensorFlow.js to do this very nicely. And my main point for saying this is that machine learning really now is for everyone. It's not just limited to the academics and researchers. We can now start to see creatives, musicians, artists, and much, much more starting to take their first steps of machine learning too. And I'm really excited to see how TensorFlow.js can be part of that picture, given how wide JavaScript is used in the community out there for many different things. And I'd love to see what you guys make as well in the future. And do share with us if you make anything. And of course, I'm available on Twitter and LinkedIn for any further questions if you don't have any right now. So thank you very much for listening, and I'll hand it back to the presenters.
Awesome. Thank you so much, Jason. That was a wonderful presentation. Lots of amazing demos. I really love that the conclusion, which is like with TensorFlow.js, we are just democratizing the machine learning or AI part of the web revolution. Like as web came in and revolutionized the whole industry as we see right now, with TensorFlow.js, we are seeing that same thing happen again.
Yeah, it's reaching like a second wave right now, and people who are jumping onto the JavaScript bandwagon right now are a very exciting time to have a lot of influence as well. And I hope to see more collaboration, honestly, between the Python communities and the JavaScript ones. Like as I mentioned, we can run the saved model format in Node, and it would be lovely to see more of the academic folk exposing their work to the web environment, so people can start using it in ways they've never even dreamed of. I mean, people are doing teleportation and all these things, right? And maybe that was the initial use case for body pics, but things like this can be now made, and with a bit of creativity, new things can come to life like this. So I'm really excited to see where that can go in the future.
Yeah, that's amazing. One of the questions that we got on chat was, why would you want to choose JS versus Python and R? And I think that you covered some of those things, but if you want to go into more details.
Yeah, I don't want to force any language biases on people here. Use whatever you're familiar with, of course. But I mean, the benefits that I spoke about today, such as the ones in the browser where you can get privacy or lower latency or more cost savings, these are the main reasons you might want to consider deploying to the web. If those things are important to you and your use case, then that might be a good reason. Or maybe you're looking to get a little performance boost for the pre and post processing. Maybe Node.js is a consideration for that kind of stuff. But honestly, you can do stuff in any of these languages and use what you're familiar with. But if you are going to integrate with other teams, then maybe consider exporting the safe model and allowing it to be digested by people who might want to use JavaScript or something like this.
Yeah, of course, yeah. That is like the great way to do it. You can not only build your new models with TensorFlow, you can also use existing models that are built by your other team members. Yeah, awesome. Thank you so much, Jason.
Thank you very much for having me. Cheers.
Pass it on to the next presenter. Thank you.
Bye-bye.
Bye.
I think we're supposed to have a raffle right now, aren't we? Bruce. Okay, I'm not sure how we're doing that. I don't have the tool to do that. Anyway, I'm just going to go with my stuff and we can maybe sneak that in afterwards. Anyway, I'm Jerry Kurata, and I'm fortunate this afternoon to moderate the section on TF Lite, which is a library that'll let us expand our machine learning to mobile and edge devices, both of which are big growth areas. To start off this section, Margaret, are you going to do the raffle?
I could.
No, that's okay. I'll just go. Sorry, guys.
If you could do the raffle, you just bring up a Chrome screen and go to that wheel of names.com.
What is it? Wheels?
Wheelofnames.com.
Okay. I'm not seeing anything here. Let me share my screen.
It's okay if you want me to do that.
Yeah, if you wouldn't mind doing that.
Yeah,
I'm not. I don't think I'm set up for it. Sorry, guys.
Yeah, it's okay. I'll do that.
Okay. Should you want to do your talk first, or?
No, I think we should run the raffle because last raffle was at 2.
Yeah.
So I'll just share my screen. So, okay. Okay, so I'm gonna remove everything here and hope everybody is ready for the raffle. Let's see. Okay, nobody says, okay, I'm too late, or give me a minute. All right, nobody said anything. I guess everyone is ready. Okay, we'll just go here and import the Twitter users. As before, we will use the DevFest West Coast 2020 hashtag. And get everybody who has tweeted with that hashtag. Whoa, look at the list.
Yeah, I know. It's getting a lot bigger, isn't it?
Or yeah, as big as before.
Yeah.
So we're gonna do 2 like before. The first one will be a DoorDash $25 gift card. Second one will be a Google Play card. All right, everybody ready?
Go for it. GTH, is it? Oh, G1H.
Yeah, G1H. Whoever that is, like I said before, please just contact organizers on Eventbrite so that we can get your name and email to send you the card electronically. So that's the first one. Now we're going to do the second one. Hopefully there's no additional tweets. And somebody said, just spin the wheel. All right, let's spin the wheel. Busy hacking.
Busy hacking. What a great name, huh?
Yes, I like that name. So congratulations, Busy Hacking.
Yeah.
You got a $25 gift card.
Cool.
All right, so that's our raffle for this time. And the next raffle is going to be at around 5:15. So if you haven't done it, make sure you use the DevFest West Coast 2020 hashtag.
Thanks, Margaret. So anyways, like I said, I'm Jerry Carrata, and I'm fortunate to get to moderate this next section on using TensorFlow Lite to expand our machine learning on both mobile and edge devices. We have a couple of presentations on this. Our first one will be done by Margaret. So let me just introduce her. You have seen Margaret doing all this management and things of this behind the scenes, but she's also a organizer of one of the largest communities, which is GDG Seattle, which hosts a lot of events throughout the year, which we mentioned earlier. In addition to that, she's an accomplished author. She has written many articles on machine learning development, including a recently published series of articles on how to use TensorFlow Lite on your phone to create anime versions of selfies. It's really cool, and I suggest you all check out the Medium article and check out her code. But even as busy as she is, Margaret is constantly helping other people. And to help us today, Margaret is going to go over TF Lite and its awesome tools and community that will make your TF Lite experience enjoyable and fun. And with that, I'll let Margaret take it away.
Great. Thank you so much, Jerry, for the introduction. You know, like Jerry said, we are part of the Google Developer Experts, GDE, Machine Learning GDE community together. So we've worked with each other. And today, I am very excited to share with you about TensorFlow Lite. So I will discuss about what is TensorFlow Lite, why we need it, and mostly focus on how to use TensorFlow Lite. And then I will spend some time talking about the community, the awesome community. With TensorFlow 2.0, the whole model saving has been standardized into the save the model format. You can still save as a Keras model, but we recommend you use save the model, which you can deploy to clouds, web, mobile, IoT, microcontroller, and edge TPU. So TensorFlow Lite is a framework and with a set of tools for deploying machine learning to mobile and embedded. You know, unlike earlier when you heard about some talks on TensorFlow JS, you know, JS, it's also a language you can use to write your models, right? But TF Lite, it's a framework of tools to help you to deploy. It's not something you use to write your machine learning training code. And there are many components. There are the key components. One is a converter for converting to the .TF Lite model format, and then the interpreter that you can use to run the inference. And then there's TensorFlow Lite Ops, and then also interface to hardware accelerations. In addition, there are also some other features and tools in addition to these four main components that I mentioned. So why do we need TensorFlow Lite? So when we run machine learning model on device, we get the benefit of access to more data, faster user interaction, and preserve privacy. But there also comes the unique constraints of less compute power, limited memory, battery consumption, and you have to worry about the model size and inference speed. So TensorFlow Lite was created to help deploy models to mobile and edge devices in order to work with all these constraints that I just mentioned. So today, there are more than 4 billion devices and more than 1,000 plus apps in production running with TensorFlow Lite. And how do we use TensorFlow Lite? Well, there are these beginner getting started topics, and there's also advanced topics. So to get started, we talk about like how do you save the model and do the model conversion. And also for people who are not so familiar with machine learning, there's TensorFlow Lite, Model Maker, and metadata and code gen, and also the model ML model binding. Android Studio also helps with like using the TF-Lite model in Android. So these are the beginner topics. Some more advanced topics will be how can you reduce model size with quantization and pruning, and how do you speed up the inference with GPU delegate using Android neural network API, how do you do benchmarking or profiling. So today, my goal is to more help you get started, as well as talk about some additional resources that comes from the community. So first, let's take a look at a very simple example, end-to-end process, going from training a model with tf.keras and convert that model to TF-Lite, and then run that model on Android. Very simple. So from this diagram, you will see that when you train the tf.keras, you have the option of using the keras sequential, functional, or model subclassing. And when you convert, you can use either Python code or you can use command line. And then here's all the steps of how to run it on Android, which I will go over the details later. So this first example is very simple. We use MNIST data. For those of you who are not familiar with machine learning, the MNIST data is what people will use for the hello world, like 60,000 training data set, 10,000 test data set, and 28 by 28 grayscale images with 10 classes, ranging from 0 to 9. And we can also use it for benchmarking machine learning algorithms. I have included the Colab here for writing the training code. You import the data, you define the model architecture, you train the model, and then we save and do the conversion. And in this particular example, we're saving as a keras model format and before we do the conversion. So once you write the code, you can call model.summary to show the model architecture. And the reason why I'm showing the model architecture is like a lot of times when you're working with like the conversion, you need to know, or even the model implementation, you need to know kind of your input shape, right? You have a data input to the model and then also the output. To visualize the model, you can use visualization tools such as TensorBoard. I use Netron. This is like an open source tool that once you install it, you just drag and drop the TF-Lite model into Netron, and then you will see the model visually. So there's later on I will talk about the metadata, which is a new TensorFlow Lite tool. It will also allow you to inspect the model. So once you train the model, it's a simple example, so I didn't really show the training code there. But once you train it, and you can save the model, and you can save it to either save the model or keras model. In TensorFlow 2.0, the saving methods actually will default to the save the model format, not the keras model format. The save the model format is recommended. When do you use which? Especially if you are sharing a pre-trained model on TensorFlow Hub, for example, you definitely need to use the save the model format. And it's also useful if you don't know the deploy target. But let's say, in this case, I'm just writing a very simple example with MNIST. I know what my deployment target is to Android. I'm writing the training code, I'm saving it, and I'm converting it. So I just use keras. And I'm showing you the example where we have two options to do the model conversion. You can either use command line here, or you can use the Python code, which is recommended. Again, when you try to save, you can do save the model or Keras model. So the command line method will be helpful. Like, for example, if somebody else has trained the model and gave you the model, so all you have is some model format, like save the model or Keras model, then you will run the command line to convert that. But the Python code, writing the Python code to do the conversion is recommended. And here is a very simple example that you create a converter and you set the quantization to be true, and then you will convert the model. And then after that, you can try, say, if you're in Colab, you create the actual TF-Lite model file, and then you can download the model files. So for those of you who have actually worked with the TF-Lite for a long time, you probably remember a couple of years ago trying to do a conversion was not as simple, with just a few lines of code. And back then it was like really complicated. So now you have converted your model and to the TF-Lite format. Before you deploy it and after you convert, it's a really good practice to try to validate the result and make sure that the conversion process didn't really mess up your model. And you can look at the TensorFlow inference and also the TensorFlow Lite inference, and then compare the results. So now that we have a TF-Lite model, here's how we will implement it on Android. And I know not all of you are Android devs, but I'm still going to go over the steps just to show you how complex it is. So manually, you have to do a lot of manual work, right? You have to put the model under the assets folder, update the dependency, the input, etc., etc. So dependency, we have to come here. In Android Studio, we have to manually create an assets folder, put the TF-Lite model there, and then we will go to the build.gradle to manually set a bunch of dependencies to TensorFlow Lite, or like if you work with metadata, you will set all those dependencies, and also for example, set to say not compress a file if it's a TF-Lite format. And if we have an input image, in this case, if we're working with MNIST data, the digits, when you have the image that captured either by drawing on canvas from a custom view, or getting an image from the photos gallery, or getting an image from a third-party camera, or live frame from, say, your camera API, right? After that, you have to make sure, earlier I talked about the model is trained with 28 by 28. You have to make sure your input image is like that. And also depending on what kind of model we're talking about, if it's Inception or MobileNet, etc., you have to match up the input shape. And then there's image preprocessing to convert from a bitmap to byte buffer, because that's what TF-Lite works with. You have to also normalize the pixel value to be a certain range, just like what you do in the model training. And you need to also convert from color to grayscale, because when you use the camera or the input methods, as I mentioned earlier, they have other several options that all have images in color. And then because the model was trained in grayscale, you have to do that conversion. And then to run the inference, you have to load the model, the TF-Lite model that's created under the assets folder. And you have to also load create the interpreter You then run the inference, and which will give you some sort of results. And it's like an array of probabilities. Each correspond to a category. In this case, we have 10 categories going from 0, 1, 2, 3, etc., to 9. And then you'll find the category with the highest probability and then output the result to the UI. So this is the example code here. It's a digit recognizer where I will draw with my finger, like a number 8. And this is a custom canvas. And then you click on the classify button, and then the model will predict it's an A. So I just walked you through an example with MNIST, which is a toy example. The model architecture is super simple. The data set is super simple. So training with TF.Keras is fairly easy. I didn't even include the code earlier because it's just a few lines of code. Model conversion to TF-Lite was also fairly easy, as I showed you earlier, either via command line or Python code. Either way, it's just a few lines of code. But the Android implementation was a lot of work. You know, you don't have to understand Android to understand what I explained to you earlier with all those manual steps of placing file in there, dependency updates, and worrying about image pre-processing, input tensor shape, if it's a color or grayscale, post-processing, etc., right? Anyway, so I have included my blog post there for you to read in more details. So how can we make it better? You know, what I just described to you, especially the Android implementation, was very complicated. At TensorFlow World last year, there were quite a few new features announced, you know, like the TensorFlow Lite support library, the metadata, the model maker. You know, later on, I will also talk about the ML model binding. And all of these will make it much easier to work with TensorFlow Lite. So I will talk about the metadata and the code gen briefly. You will use pip install tf-lite -support, this library. It will provide you with two functionality. One is metadata, which this will contain information about the model. I didn't include the details here, but you can run it through a command line script. Currently, the metadata examples, you know, if you go to the official tensorflow.org documentation, you will see the script for image classification. I think it's not posted yet there, but what's available or supported, it's also cell transfer supports the metadata. And later on, I will talk about a example that I'm working on called a selfie to anime. So we can also use metadata for GANs or image to image translation. So what it does is that you either run it through command line or maybe in Colab. The tool will help to add a bunch of information about your model, like for example, the input shape and what the model is about. At the same time, it will enable the code gen, which is the automatic code generation of Android wrapper for using of the TF-Lite model. So earlier, I mentioned to you a lot of really manual process, and all of that will be taken care of by code gen. So you don't have to do a lot of that manual work. So I wrote a two-part tutorial to demonstrate those two features. To demonstrate the code gen and the metadata and code gen, but through the ML model binding from Android Studio. But the first part is actually using another tool called the TensorFlow Lite Model Maker. So what it does is that when you do the machine learning training, you actually have to worry a lot about the data loading and pre-processing, which is really hard in machine learning. When I showed you the toy example of MNIST, you don't have to worry about it because that toy example comes with part of Keras, right? It's just one line. You can load the data. Or when you use, say, TensorFlow 2.0's TFDS, there's also ready-made data. And if you use Kaggle, the data is, you can also find a lot of very nice, clean data, right? But in the real world, when you work on your own machine learning model problems, that you may spend a lot of time in the data pre-processing part. So the nice thing about the TensorFlow like model maker is that you don't have to worry about the data processing part. All you have to do is just point to your folder of images or files that you have, right? So the input can be TFDS, can be Kaggle, can be something you download from the internet, or the pictures of your cat that you took, right? All you have to do is point to those folders. And then just with a few lines of code there, and you can create a model currently supporting image classification or text classification, and it's default to efficient net, but you can also change it to be MobileNet, ResNet, or a particular model that you find on TF Hub. So it's quite versatile. And another nice thing about this TensorFlow like model maker is if you use the model maker to create a model, by default, the metadata is already part of that TF-like model that gets generated, right? So earlier I mentioned to you to get the metadata added to the TF-like model, you can either run a Python script or you can write some code in Colab to do it. Either way, you have to write a bunch of code, quite frankly, very boilerplate code to add that metadata. But TensorFlow like model maker does that all for you. So once you have a TF-like model with that metadata, and when you're in Enter Studio, all you have to do is go through some path to say, import my model. And once you import that TF-like model with metadata, all the manual step that I mentioned to you of placing the model manually under some folder, you don't have to do it anymore. That manually going to build.gradle to update the dependency, you don't have to do it anymore. And to write all the code to load the TF.TF-like model and run the inference, you don't have to do anything. Like, you don't have to do much to use that TF-like model other than just a few minutes going through the menu path and import and done. And it will also give you some code snippets where you can copy and paste and directly use in your model. So now I'm going to switch gear to be talking about community. And so as I said, 2019, the model conversion got much better last year. But a bunch of improvements was made, but we don't have too many end-to-end TensorFlow like sample just yet. But now, fast forward to now, we actually have a dedicated repo under the ML GDE on ML GDE org on GitHub. You can find that there's a list of sample app ideas and projects that you can help with. And I only took a screenshot of the top part of it, of the project ideas and help needed. But on that GitHub, you actually will find like in progress and the completed end-to-end tutorials. And you can help with the existing proposed ideas, or you can propose new ideas. And you can help with creating the model, converting the model. You can help with writing iOS, Android, or implementing the model, say, on an edge device. And I want to talk briefly about Selfie to Animate, which is the first of the series of end-to-end TensorFlow Lite tutorials I just mentioned. And this was a collaboration, me collaborating with another machine learning GDE Sanyak and Khan David from TensorFlow Lite team. And this is a state of art. If you look at this link that I put here, you will see that the repo has like 4,000 stars on the model, the paper repo. And it's image-to-image translation with GANs. However, even though it's state-of-art and it's new, the code, the model training code was written in TensorFlow 1. So this end-to-end tutorial actually gave the example of how to save the model in TensorFlow 1.0 and then do the model conversion in TensorFlow 2.x, and then run the inference in Python as I said earlier, and then add the metadata and run the benchmarking tool, and then finally implement it on Android. So I will put a link of the Selfie to Animate project so that you can check out the details here. And I also want to talk about, my talk title is called Awesome TF Lite. There's this awesome list that I put together with all the TensorFlow Lite models, apps, tutorials, and learning resources. And you can check it out. The machine learning GDE and Android community really helped out with this repo a lot. And we also have support from the broader community. And also thanks to the TensorFlow Lite team for their help with this. So definitely check out this. And a few things that I did not mention in this talk because I try to compress it. If you go to the Awesome TF Lite repo, you will also find resources to things such as ML Kit. You can try implement your model, TF Lite model with like media pipe, with third-party SDKs, for example, Fritz.ai, and just a whole lot more like books and the videos, etc. Some additional resources before I close my talk today. And I want to just give a shout out to Machine Learning GDE Sanyak Paul. He has this adventure in TF Lite repo, and where he goes in depth to talk about quantization, saving and converting the models. And just today, GDG Kokada, Hoi Lam from Google also gave an excellent talk on Android ML. I encourage you to check that out. I still need to watch it, but I'm sure he'll be talking about all the new features with Android ML, including how to use Firebase and ML Kit, etc. And then a blog post by Khan David called "What's New in TensorFlow Lite" from the TensorFlow Dev Summit 2020. So he will also go in depth talking about a lot of the new TensorFlow Lite features from this year. So thank you everyone for listening to my talk, and please keep in touch. Follow me on Twitter, Medium, and GitHub to learn more about deep learning, TensorFlow, and on-device machine learning.
Okay, Margaret, thank you. Thank you very much. Let's see, a couple of questions here if you have a moment. The model maker sounds like a really cool piece of code. With it, how long, if somebody knows what they're doing already in Android, would you say it takes them to get like their first couple of models up and going?
That is an excellent question. In fact, somebody has asked me that question. Android GDE asked me a question. An Android expert asked me that question. And here's my answer. There's also this teachable machine. I think earlier might have got mentioned in earlier talks. So I want to compare and contrast those two. With the model maker, I will say if you don't know machine learning, it is still a bit challenging, in particular if you don't know Python that well, right? But if you know Python very well and you're taking some beginner machine learning classes, like you have some general idea of deep learning, image classification or text classification, it's very, very easy. But if you don't know Python, you have no clue about machine learning at all, then I think it's challenging. Then I would recommend you to use more of the tools that's more like web interface, drag and drop, like Teachable Machine, or there's another thing I didn't mention in my talk, but I usually mention in my previous talk, which is called the Edge, what is it called? The new Vision Edge as part of the ML kit or the Google Cloud. So I think it's Vision Edge tool that I'll find the link and share with you. So share with everybody. So basically use this. People who don't know machine learning at all, it's better to just use the web interface, drag and drop.
Are you seeing a lot of, I know you specialize in Android and things like that. Do you see a lot of Android developers trying to build machine learning into their applications?
I think so. Again, I think I'm going to add to my, later on, I'll add a link to my slides, is that, so there's this TensorFlow.org. If you go to TensorFlow.org, look for the community tab. So there are different communities, right? There's TensorFlow JS, there's documentation, different one. So there's this community called the TF Lite, right? So I'm part of that community, so I will see the questions that comes in. People will ask TF Lite questions, right? And from what I've seen last year versus now, I see so many more questions about.
Oh, that's great.
About how do I do XYZ on Android? How do I do XYZ model on Android? Like ranging from people who know machine learning, who don't know a whole lot about mobile, or just mobile developers. They want to put something on a TF Lite model on Android.
Okay. We do have one question that just came in. Somebody asked, let's see, Greg here, is MediaPipe working well now in Android? I don't know what MediaPipe is.
So I will take that question. If you follow me on Medium, you will see one of the articles I wrote about is getting started with MediaPipe on Android. When you say working well, I will say MediaPipe works pretty well on Android. Like if you go to the MediaPipe GitHub, you look at their examples, they work extremely well. In fact, some of the complex model training in MLKit under the hood is actually powered by MediaPipe. And MediaPipe is excellent for you to work with things like multi-hand tracking, like really heavy-duty kind of complex models. But if your question is it easy to get started for Android devs? I will say not so much, because just read my blog post, because I don't think it's that Android dev friendly to get started. But does it work well on Android? Yes, it works very well on Android.
Okay, great. One other thing I guess we probably should mention is you're kind of Android specific, but most of this still works in the iOS community too. Is that not correct?
That's an excellent point. Yes, because my talk, I talk a lot about Android. I will say TF Lite in general, like if you create a TF Lite model, a lot of the process I mentioned should work with iOS. However, not everything. For example, the ML model binding, the thing that I mentioned, you go to Android Studio, you just click a button to say import my model.
Right.
That only works with Android at the moment.
Oh, okay.
So yeah, there are certain things only work with, some of the tools only work with the Android, but TF Lite in general, the model format in general, like yes, it worked with iOS and it worked with Edge TPU, which the next talk is about. Right.
So it sounds like maybe the iOS side is a little in trail, and I know the Edge one is a little more scriptish than let's say.
Yes, I will say,
toolish.
if you look at my example, actually, I didn't include a whole lot of examples. But if you go to Awesome TF to look at examples or the official examples, you'll tend to see there's a lot of like image examples. We're still catching up with the text examples.
Yeah. Okay.
So it's kind of like that. We might be catching up a bit with the iOS part, but I will say right now, the TensorFlow team has made a lot of progress in that area.
Okay, great. Let's see here. I don't see any other questions. I guess I would suggest everybody go and take a look at Margaret's awesome TF Lite repo. I've looked at it. I don't claim to be an Android developer by any stretch of the imagination. I've done some, but not a lot. But it's helped me, because I come from a Python background, be able to move things over and to understand some of the little gotchas that you have when you work these small systems, such as, dealing with memory and that sort of thing, and that you have to think about maybe different than, on a small phone device or even smaller. Okay. Let's see. I guess thanks, Margaret. Do you have anything else? I guess that's it then? Okay.
Yep.
Well, our next talk is we have Naveen. Is he up on the list there? Good. So Naveen, we're kind of, hey Naveen, how are you? Let me introduce you.
I'm doing good. Yeah, please go ahead.
Well, we're having a little bit of an audio problem there with your audio.
Can you hear me now? Fine.
We're getting a little feedback, I think, or something like that. Maybe it's just me. Let me finish up the introduction, and then we'll see how we go. How's that? Okay. So we have Naveen today. Naveen's from the Google Coral team, and he's going to speak to us about the Coral framework and devices. Coral is a complete toolkit for building products for local AI capability that is efficient, fast, and offline if required. Naveen has a master's degree in intelligent systems, and on the Coral team, he works as an application engineer, helping customers migrate their applications to the Coral platform. And when he's not helping people bring AI solutions to the edge, he lives on the edge and does horseback riding and motorcycles. And with that, Naveen, I'll turn it over to you.
Thank you. Thanks for the introduction. And can you guys hear me well right now?
You're still we're getting a little feedback, maybe? I don't know what that is exactly.
Yeah, maybe we still have like 4 minutes to start. Let me get my headset good.
Well, Naveen's doing that then. If you guys have any questions, please put them in the, let me do that. Put them in the, the thread there, and we'll go ahead and answer them. Hopefully he can get his distortion fixed up and reconnect and things like that. I'm not quite sure what's up with that. Maybe the internet gods are just not working well with us today. But anyway, we'll get that sorted out here in just a moment. So how many of you have ever looked at, have any of you looked at the Coral products and things like that? I spent some time with them and things like that. In fact, I have one. Let me just show you that here, just to fill in. They are this little board here that I have, which is exactly the same size of a Raspberry Pi. This case actually that it sits in is a Raspberry Pi case. So if you're familiar with one of those, it's capable of doing some pretty fantastic things. You've probably heard of Google, has these TPUs and things like that, and they've been able to shrink it down to some sort of, I don't know how they did the magic here, but you can kind of see the processor in this device, and it's smaller than your fingernail, your little, pinky fingernail here, and they're able to get TPU-like performances. So it's amazing that they can do that. I don't know how they do it, like I said, and but I've seen this particular device when I was doing object recognition run up to like 65 frames per second, detecting objects in a video stream. Oh, looks like Naveen is back. And so...
can you hear me better now?
Oh, much, much better. I'm going to drop off and let you give your presentation.
Sure. I'll take on from here.
Yeah, you're up, so go ahead and start whenever you'd like.
Oh, sure. Hello, everyone. Thank you for joining us today at DevFest West Coast. I'm from Coral team. As Kyle introduced me, I'm an application engineer helping customers to integrate their solutions onto Coral Edge TPU. So I'm going to explain today introduce you to Coral devices, explain the ecosystem around the Coral device, and what are the hardware requirements that you need to use a Edge TPU and run inference of an AI model at the edge. So let's start by knowing why we introduced Coral. So the main reason why the Coral platform is built and developed is to democratize machine learning and also provide a lot of privacy for the users at the edge. With increasing in the privacy concerns, running AI at the edge is the most important thing. So Coral platform provides privacy and accelerates the machine learning applications by saving a lot of power, and they are efficient when you deploy them on the edge, embedded applications, saving power. And most interesting thing is of Coral all the AI applications are offline, and you can run these without internet. Especially in a life-saving situation, you should not be stopped by internet for AI applications. So what Coral platform consists of? It consists of some hardware components and software tools as well. So if you're taking a look at hardware components, we have Edge TPU modules available in different form factors, M.2, PCIe, and USB connections. And we also provide some ambient sensors to sense audio, video, and environmental variables like temperature, moisture, and also motion sensors to detect any fault detection like that. If you're coming to software and ML tools, we have OS called Mendel, which is used on the Coral dev board to which binds up the Edge TPU and the other peripherals around it. And considering ML tools, we have a compiler that converts an TF Lite model and maps all the operations to Edge TPU, and which take care of switching the workload back and forth between CPU and Edge TPU. Of course, we do have documentation for all these, providing data sheets and schematics to develop your own applications, and also a huge list of example projects, which can be a great resource for you guys to start prototyping your projects. So these are the current products available right now, distributed around the world in 36 countries. DevBoard and USB accelerators are two of our prototyping devices, which aren't designed for production, but we have seen a couple of customers going into productions with these devices. But these are designed for prototyping. And we do have a SOM module, which is a system on board. Technically, this is a dev board without any peripherals around it. So we provide you schematics and all the information needed to fit this into your own embedded applications. And we do have a PCIe accelerator form factor, which can be chipped into your local host machines or your industrial PC, enabling your industrial PC to perform AI at the edge. And PCIe accelerators are industry-grade accelerators, helping the users to make sure they can build AI at the edge in the industry scale. We also have the camera module, and which is a MIPI interface, and environmental module, which gives you information about the light, humidity, which can be used for IoT applications. yeah, and this year at CES in the Vegas, we announced 2 new products. One is DevBoard Mini, the same version of the DevBoard that you see on your website, but it's a very low power form factor and a small CPU, but still uses the same edge TPU. And bigger memory versions of the soundboard, 2 gigabytes and 4 gigabytes. And we are also looking at developing 2 gigabytes and 4 gigabytes dev boards as well. But all these chips have the same edge TPU chip embedded on it, which consumes about 2 watts, delivering peak performance of 4 TOPS. So here is an upcoming product of us, which is called Edge TPU module. So this is a shoulderable version of Edge TPU, which can be shouldered by USB 3.0 interface or mini PCIe interface. So this is another in the production module of the Edge TPU, and yeah, this comes along with the PMIC and everything integrated in it. This was developed in collaboration with Murata. Cool. So now let's see our software and software libraries. Officially, we support a Mandel OS. Mandel OS is on the DevBoard and DevBoard Mini, which is based on Debian Linux. And so this platform is used by most of our prototyping solutions, which isn't recommended for production. So for production, we support Yocto and Android, which can be built on the same DevBoard and used in production. So runtime, Edge TPU requires TF Lite runtime on the embedded devices. It can be either with USB or PCIe or any form factor. Every form factor requires the same runtime developed by TF Lite. So we currently support ARM-based architectures and AMD architectures. So most of these, all these runtimes are built in Linux so far. Very recently, we started supporting Windows as well for USB and PCIe form factors. Sorry. So to run inference, we use a TF Lite interpreter on which can be installed using pip and supported by the TF Lite workflow. So all you need to do is import a TF Lite interpreter and load the Edge TPU delegates to run it. So coming to software and models, which is the main part of enabling machine learning at the edge. So the compiler and the runtime are the downloadable versions, which are used to enable inference at the edge. And we do provide a huge list of checkpoints and Edge TPU models for users to build prototypes or to do experiments with our existing models, which includes state-of-the-art networks like MobileNet, ResNet, InceptionNet, and all. And we do facilitate on-device transfer learning, which is performed on the CPU. And we have a quick start pre-compiled models and transfer learning. Transfer learning can be done in Google Colab or in AutoML anywhere, and then compile the models and pass it to the Coral board. So most of our software documentation is located in coral.ai. Coral.ai is our official website where you can find all the software documentation and the models and the resources to get started. And we do have sales from that website. So here are some fun results of the performance of Edge TPU with regular CPU and also the DevBoard CPU. Considering a model like MobileNet V2, an average inference time with an input size of 224 by 224 is 2.3 milliseconds. So considering that you see around 300 frames per second on a video stream. If you consider ResNet, you see about 48 milliseconds of latency. So these are the so far we have benchmarked these models, and we are in process of benchmarking other models as well. So if you take a look at AI's model Zoo, you can find more models of Edge GPU. So now I can walk you through a couple of examples that we have developed so far, and why you can see why we use the importance of doing inference at the edge. So as I said, inference preserves the privacy of people and enables you to know what's going on. So if you're taking an application, this is a smart city application, and you do want to see the mobility of people and see how many people, see the traffic flow, you can perform edge inference and preserve the privacy on device and just get the results of how many people. The same thing here. So analyzing the density of the cafeteria, you need not upload every frame to the cloud to see the results. Yeah, all you can do is perform inference at the edge and just push only the results to the cloud. So this cut down a huge bandwidth from gigabytes to bytes. Considering a 4K or a HD video frame, you're saving gigabytes of bandwidth every single day, just from one single camera. This is another application to monitoring traffic flow. You'll have this is another on-device application where you'll continuously monitor the traffic flow. In this case, the speed is important. So if you're waiting on the cloud bandwidth to get the results from back and forth, there is a lot of latency just because of the cloud. So if you're able to perform edge inference, you're able to get around 70 to 80 frames per second speed. So these are the applications so far built by the Coral team. But if you're looking to do your own and follow most of these applications, here's how you do it. This is our official GitHub handle, Google Coral. You can visit this page, and we do have a number of tutorials and example projects that we have done so far, of which Coral BodyPix is very famous. You can detect the pose, anonymize the users, and get their body information, like the pose information, detection, and the segmentation, all at the same time. Yeah, please feel free to check it out. The BodyPix is a very famous application of ours. And recently we have even released a project Banana Robo. So this project motivation is to interface Coral Edge TPU in the USB accelerator with a Raspberry Pi. This is so feel free to check out the GitHub handle, and this is a great it has great resources which can be a start point for your prototypes or projects. And you can reach out to our team from there if you have any questions or a special request. So, so these are the two examples what public has been doing. There is one of this company called Neuralnet, which recently developed a social distancing model using and running the inference on the edge device. So they developed this application, and to preserve user privacy, they're performing inference on the edge device and uploading the results to the cloud, and to make sure everyone is following social distancing. And one of our team member has recently developed a face detection model and deployed it onto Coral, and it works out pretty well. We get the performance of close to 80 frames per second. So as you have seen a lot of applications and examples, I'm sure you must be curious to know how you can compile a model to deploy it on edge TPU. So Coral edge TPUs are AI accelerators that support only integer format of the weight. So to do that, you have to train a model, test it, and then freeze a model. Use post-training quantization using TF-Lite converter. You have to convert it to apply full integer quantization and convert it to a TF-Lite file, TF-Lite model, and then using our compiler, map the operations to edge TPU, and then deploy it to a hardware. Yes, this graph might be a little unclear, so I'll walk you through the next steps slowly. So after you train your model in TensorFlow or Keras, in any other platform, you take the TensorFlow model, which has the weights in float 32 or float 64, and quantize the model to run on edge TPU. And considering the fact that Coral devices right now only support inferencing, they do not support any training or any other thing. So once the model is frozen and deployed on the Coral, you cannot retrain the model. So the model has to be frozen before going to the quantization step. So here quantization can be done in 2 stages. One is post-training quantization, which we see most of our customers do. After the training process is completed, they take this training graph and calibrate the weights using a representative data set, which they have used for training and testing purposes, and then pass it to our compiler. So in this case, accuracy is slightly affected because the quantization and the calibration is not done perfectly. So we do recommend another way called quantization aware training. In this case, fake quantization weights are introduced during the training process, and in which TensorFlow rewrites the graph of during the training, assigning a fake quantized weight in parallel to the original weight. So this doesn't require any representative data set because you're performing quantization while training, and accuracy is not much affected if you quantize a model using quantization aware training. And as I said, Coral devices are designed only for the inference, and the model has to be frozen, and the batch size has to be 1 for now. So once you are done with the quantization, you pass the model, you use an edge TPU compiler to compile the model at the edge and deploy it. So this is how, if you open a edge-tpu.tflight model in a Netron, this is how it looks like. Normalized input tensor is an input tensor, and then all the operations that are mapped to edge TPU are combined into a single operation called edge TPU custom op. So this custom op runs on edge TPU. All the rest of the input and output, all the IO operations are taken care by the CPU. So in this case, this is an object detection model. It has 4 output nodes, and all the post-processing and pre-processing task is offloaded to CPU, and edge TPU takes care of running all the feature extraction task and detection task. So far, I have been talking in other applications, like how we use cloud monitoring system and how we use the results from edge device pushed into the cloud and we analyze it. But if you're looking at a total end-to-end cloud infrastructure and using edge TPU at the edge, this is how it looks like. You use Google storage buckets and store the data. Use AutoML to train your model. You can either use AutoML Vision or Vision Edge or AutoML Vision Video Edge. So use the services to train your models on your data, and then use IoT Core to push the trained model onto the edge TPU and run inference. Once the inference is being done and you save the results that are pushed onto the cloud later, depending on your priority when to be pushed up, and you see the results without any user data, without any private users data. So considering such an end-to-end pipeline using cloud and edge deployment, here you save a lot of bandwidth and also provide a lot of power or privacy to the users. And this enables to efficiently use our current data centers to store the required data, and also efficiently use the power for performing AI inference. Considering the fact that the footprint that's left by running AI operations is considerably large, the carbon footprint. So using a low power device to at least to run in inference and save power is a lot of useful. So we do have a cloud monitoring demo on our GitHub page, so where it provides you all the tools and the scripts that are required for an edge deployment and also cloud interface. So you push the data to Cloud IoT Core and then use Dataflow and BigQuery to analyze your results. And of course, you can deploy the results to a web front end and see what's going at the edge. So before taking off, I would like to show a quick I would like to show you a quick tour over how we can use how we can deploy it. So here I'm using a I'm using a Colab to run to compile a edge TPU, to compile a model to TFLite and then to edge TPU. First of all, let's install a HDPU compiler. So these instructions can be found on coral.ai, the website. So once, meanwhile, we can talk about the TF-Lite conversion API. In the previous talk, you guys are introduced to TF-Lite convert API and also TF-Lite command line API. So for this demo, I'm using a command line API for this. So I have trained and exported object detection model using object detection API, and I've froze the model with normalized input tensor as an image input tensor, and all these 4 as an output tensors for an SSD model. So yeah, once I have my frozen graph, and if I mention an output image and provide all the details of input arrays and output arrays and specify the inference type as 8-bit integer, you're all good to go. And so this just takes less than a minute or so. We do currently Coral devices support only 8-bit integer operations, and we do support multiple input and multiple output arrays. Yeah, so the conversion is done, and the graph is quantized and saved as a TF-Lite file right here. So yeah, that's it. And the next step is to compile the TF-Lite file using an HDPU compiler. So after compiling a model to HDPU using an HDPU compiler, this creates a model called with a suffix called hdpu.tflite, which also deploys a log of sharing you information of how many number of operations are going to run on the CPU and how many number of operations are going to run on the TPU. So this is an MobileNet SSD model which is developed and trained for mobile applications. So all the operations are mapped to HDPU, and only one operation is running on the CPU. That means we are using HDPU acceleration power to the maximum, and we can get a maximum performance out of it. But if you see, half of our operations are running on TPU and half the other operations are running on CPU, there is good amount of latency involved in the IO operations, pushing the data back and forth from CPU and TPU. This increases the latency. So when you're developing a model for edge TPU, one thing that you have to take care is to develop a model which are supported by edge TPU, to develop a model with all the operations supported by edge TPU to leverage maximum performance from the edge TPU. Yeah, this is how you deploy a model. But once you deploy the model, you're good to go onto the running inference on the edge TPU. So at last, I do want to introduce you guys to our website, coral.ai, and yeah, you can visit our website, coral.ai, and take a look at the products available. But here's the information of all the documents of and the guide for dev board or USB accelerator or anything. And here's the model compatibility issues. These are all the list of operations that we currently support on edge TPU. Any other operations of this list is offloaded to CPU, and CPU will take care of it. But if a model has most of these operations, the entire model can be mapped to edge TPU, and you can utilize edge TPU resources to the maximum. And we do have the pre-compiled models. So feel free to take a look at pre-compiled models and download. So this is how our TF-Lite runtime works. The entire model is mapped to CPU and edge TPU. The part that runs on TF-Lite runtime will take care of splitting the model and running it on edge TPU and CPU. With this, I'll open up. Thank you so much, and I'll open up for questions. Yeah.
So we have one here. It says, let's see, what would be the performance if I do body picks directly on PI using TF-Lite versus USB? I think he's talking about the Coral USB board. What performance delta would you expect to see using that? Let's see here.
Sure. So
yeah, running the Pi versus with or without, I think, is the net.
So if you're using a USB accelerator, you definitely require a host CPU. It can be Raspberry Pi or laptop or any host CPU. So, and the major factor that controls the inference speed there is the model that you choose and the input size that you choose. Because we do have models with ResNet as a backbone and MobileNet as a backbone. So if you're choosing a MobileNet backbone model and you're using a regular resolution like 480 by 640 or 320 by 320, you're looking at a real-time performance close to 40 frames per second or 50 frames per second.
Okay.
But if you choose a ResNet backbone and a bigger image resolution size, you're looking at maybe 20 frames per second or 15 frames per second.
Okay. So, fairly significant acceleration then on that on a good, decent model then.
Yes.
Yeah. We have another question where somebody is asking about privacy concerns, just to make sure, and I kind of had this question too. In that those examples you were showing and you were talking about privacy, you had people walking and you were, like checking spacing and things like that. Now, what got sent, the actual image of the person never got sent then up off the device to like a cloud or something like that. Was that correct?
Yes. So the actual image of the person or the actual image of people who are walking is never off the device. The model just outputs a heat map of the segmentation of human beings, or just the result saying number of people present in the current scenario at the given time. So the personal data related to people never leaves the device.
Okay.
The same thing happens with the mask detection as well. If you don't have a mask, it says no, but your face will not be shown to the other.
Yeah. Because given the privacy concerns people have, I can see why you guys address that. The surveillance society type thing, things like that.
Yes.
And there was another question here: is there compatibility for things like Arduino and some of these other boards beyond the other boards? Sure.
So compatibility, we support ARM-based architectures as well. So Raspberry Pi, Banana Pi is supported. But if you're using a different OS on an Arduino other than Linux, devices are not supported. So make sure you use a Linux-based operating system, and you can build. We have recently open sourced our libedge TPU, all the libraries regarding libHDPU. So you can build the drivers for any kind of hardware platform if you're going to use our HDPUs.
Yeah, I think I saw that in some of these things where they were talking about just kind of, like edge devices in general, that you guys had given that source code, but it became then, I guess, the job of the implementer to kind of take your source code and get it running on a particular platform or something like that.
Yes.
Yeah.
So previously we aren't supporting all the platforms. Now that our library our drivers are open source, you can just build it for any platform.
Okay, great. Now, would you take contributions from people? Let's say they had some sort of chip they were working on and they wanted to, move it over to, get your accelerator running on that. Do you guys take in contributions for that?
Yes. So we do encourage such kind of things, and we have a community GitHub repo and also community page coming up. So we take contributions in that way and just publish it on the AI News.
Good. We have a question from Asim. He's saying, what excites you when you work with Coral? What sort of use cases kind of excite you about what these devices can do and things like that?
Yeah, sure. Yeah. So the most important thing that excites me is being able to apply AI at the edge in very important use cases where internet should not be a bottleneck. For example, if you take fall detection use case, so we have a PostNet model. One of our customers used a PostNet model to analyze if a person is standing, sitting, or if he fall down. So especially for elderly people, detecting a fall detection is most important thing. It has to be reported in less than 5 minutes to save their life. And in that case, if you're messing around with your Comcast or the Netgear connections, it's going to cost life. So I've seen applying Coral at many other industrial applications, making money, doing something at the edge, but saving lives with AI at the edge is something that inspired me. And I'm always encouraged by reducing the footprint of AI, because though we see many use cases of AI, I previously worked on a natural language processing application where I learned that they spent around they spent like 6 cars for training a model like GPT-2. It left a carbon footprint of like 7 cars lifetime. So yeah, training model or running an inference of AI models is extensively high power consuming computation. So if you're able to save power and use AI, run AI inference at very low power, that helps the environment as well. So
yeah. Not everything needs a RTX 2080, I guess, to process, do its work or things like that.
Yes.
Okay. Who is your competition? Somebody had asked that. Who do you see as the competition, for Coral products here? NVIDIA, maybe, Intel? The names kind of pop to mind, things like that.
So I'll answer this question as a non-Coral employee.
Okay, that's fair. Well, don't let me get you in trouble here too. If you don't feel comfortable, we can.
Yeah. So answering this question as a general public. First thing, Coral is provided by the Google research. So the main motivation of the Coral team itself, or the org itself, is to democratize machine learning and help medical applications and industry applications running at the edge where internet connectivity is a problem. So since it's a research-based organization, we are not into the competition market yet.
Okay. Fair enough. Good.
And we are very low power focused, and so far I don't see any other product any other AI accelerator in the market performing at 2 watts and being able to deliver 4 TOPS of performance.
So you can run as low as 2 watts for in your.
2 watts is our peak power consumption. It's a
that's
peak
your
power.
peak,
Yes.
not your. Wow, that's impressive. I have some NVIDIA boards, and I know what they consume, and it's an order of magnitude or so better. Yeah, than that. Okay. Well, I think that's all the questions we had for now. So thank you very much for your time, and we really appreciate it. And we'll look forward to hearing more about what the Coral team is doing, seeing more devices in the future, and getting our hands on some of this really, really cool devices and things like that you guys are building.
Yeah, sure. And I really appreciate giving this opportunity for us. And I'm happy to share more about Coral. And anyone who is listening to me, please feel free to contact us through our website. We are always excited to see new applications on Coral and always ready to help.
If somebody was building something, would the website be and they wanted to kind of show it off and get a little PR and things, would that be the proper way to go, or is there a channel for that?
Yes. So there is something called like sales form contact. So if they have already built something using Coral, they can contact through our sales form or through our support channel.
Okay.
And some of us will get back to them and share their success story on our website.
Okay, great. So that's an incentive for us to go out and build things with Coral.
Yes, you'll be shown on the Google success stories.
Yeah, well, that can't hurt anybody's credibility.
Yeah.
Okay, Naveen. Well, thank you very much then for your time.
Yeah, thank you so much.
Okay.
Bye-bye.
And let's see here. I guess Margaret and Emily, looks like you guys are up, so I'm going to drop off, guys. Take care.
Thanks, Naveen and Jerry. All right, so next, please welcome Emily Gantz from Google Federated Learning and Analytics team to talk about federated learning. I'm very excited to have Emily here because she has been giving a lot of talks over the years at our GDG Seattle event. So it's great to see you here, Emily, at our DevFest West Coast 2020.
Awesome, thank you. Thanks everyone for joining me today. I'll be talking about federated learning. I'd also like to quickly plug an event we're having this Friday. It will be a tutorial over TensorFlow Federated, or TFF. I'll be getting more into TensorFlow Federated later in this talk, but if you go ahead and go to that link, which I believe Margaret will also be posting in the live stream comments, you can register for the event and you'll get more details that way. Awesome, so let's jump into it. The goal of federated learning is to enable edge devices to do state-of-the-art machine learning without centralizing any of the user data and with privacy by default. So let's provide some intuition behind why federated learning is so exciting. Hospitals contain tons of patient records, and these are highly sensitive. Hospitals don't really want to centralize this information due to privacy concerns. So we can imagine this being a scenario where federated learning could be used to enable hospitals to keep this information decentralized and private, but still allow for hospitals to learn from this information in aggregate through things like federated analytics and federated learning. So today I'll be talking about why decentralized data is exciting, how we can make use of this data in a secure and private way through federated computations, specifically federated learning, and how to experiment with these concepts using TensorFlow Federated, or TFF. So why is decentralized data interesting? Well, for one thing, decentralized data is everywhere. There are billions of phones and Internet of Things devices that are constantly generating data. Smartphones themselves, if you kind of think about it, are the world's largest supercomputer, so it's interesting to think of them as decentralized compute nodes. The decentralized data stored on these devices could enable better products and smarter models. So can we harness the power of these edge devices without centralizing the data or without collecting this data? And why would we want to centralize this data, or why would we want to bring learning to the edge? Well, we have many of these benefits. So you see an increase in user experience through things like lower latency to prediction, the ability to use the models when the phone itself is offline. Bringing learning to the edge is better for privacy concerns as well, because the learning is localized to the device itself. This is also better for things like resource limitations like battery life and data caps, since the phone isn't transmitting tons of training data or inference requests to the centralized server. Because we're only performing on-device training when the device is plugged in and idle, we try to minimize the battery usage and performance impact on the device itself. So wow, bringing learning to the edge has tons of benefits. Why don't we just bring all of the learning to the device? It's tempting to bring just the whole machine learning process to the device itself and cut out the centralized server. But that approach itself has limitations. If we don't have a server in the loop, how do we answer analytics questions about that decentralized data? How would we continue to improve the models based on data that other edge devices have? And how do you seed phones themselves with models that are already smart, so it doesn't take lots and lots of training on that device? So that's what we'll really be looking at in the context of federated learning. So can we do cross-device machine learning and analytics without centralized data collection? It turns out we can, and that's through federated learning. Next, I'm going to walk through the basic process of how federated learning works. So let's jump into a brief example of, like, this is a pretty simple example of how FL works. So the initial model, as dictated by the model engineer, will be sent to the phone. I don't know if I have a pointer. So that's this guy. Oh, I guess it doesn't show up. For the initial model, usually zeros or random initialization is sufficient for it. Or if you have some relevant proxy data in the cloud, you could also start from a pre-trained model in this case. Next, the device that received that initial model will compute an update to that model using its own local training data. And only this update then is sent back to the server to be aggregated. None of the raw training data that was used to produce the update leaves the device. Other devices will participate in this round of training as well, performing their own local rounds of learning, each computing an update using its own local training data. Some clients may drop out before uploading their update to the server, but that's okay. Our federated learning protocol is resilient to this. So the server will then aggregate users' updates into a new model by averaging the updates together, or this is where the federated averaging comes from. The updates will then be discarded after use. The engineer will be monitoring the performance of the federated learning process through metrics that are themselves aggregated along with the model. And it's important to keep in mind that this process is iterative. New devices can check in with a server and participate in another round of training using the updated model parameters from the last round of training. And then this produces another updated model that has learned from the new client's aggregated data. Cool, so we've shown that federated learning works in production here at Google to improve the model intelligence without the need for having centralized training data or performing centralized learning. One example that I'd really like to highlight is how we've used federated learning at Google to improve our mobile keyboard. People don't really think much about their keyboard, but they spend hours on it each day. And in general, like, typing is 40% slower on a mobile keyboard than it is on a physical one. So this kind of shows how important federated learning is to improve this model intelligence behind the keyboard. Models here are essential for tap typing, gesture typing, autocorrections, predictions, text-to-voice, and more, which all greatly benefit from federated learning. So what I've shown you here are the basic concepts of how federated learning works. In practice, the process is much more complicated. Federated learning is still an active area of research. There are many extensions here, like differential privacy, compression, quantization, secure aggregation, etc. You can think of things like federated distillation or federated BERT or things like that, which are really exciting and on the frontier of research. I just briefly walked you through a very simple round of federated training, but there are many other federated computations available as well, like federated evaluation, federated analytics, etc., that provide insights and make use of your own decentralized data. So now that we're all stoked on what federated learning is, how can you yourselves experiment with federated learning? We've provided a community project for all to develop the building blocks of federated computations with TensorFlow Federated, or TFF. Here's the link if you'd like to explore some tutorials about it. It currently allows you to experiment with federated learning and other federated computations in simulation only, with more planned in the future, so stay tuned. So inspired by all of our experiences building our own production federated learning system here at Google, we've created TensorFlow Federated, but it's been generalized to be able to express any federated computation. TFF is an open source framework for federated learning and federated computations on decentralized data. So jump in and have an influence where the system goes. Because this is a relatively new project, it's rapidly evolving. And we encourage you to make contributions to it and impact the future of federated systems. So here's that GitHub link if you're interested in the code itself or if you want to contribute to it. There's many ways to get involved. So we've made TFF an open system, and this system is designed for composability to make it easy to express the kinds of computations that will enable better research, etc. We hope it will allow researchers to better understand what works and what doesn't work in a federated system, and it will help federated enthusiasts develop faster together, and it will create an ecosystem for new applications or deployment environments. So speaking of deployment, TFF compiles all code into an abstract representation, meaning that it's architecture agnostic. Currently, this is only available to be run in simulation, but someday we'd like for it to be able to be deployed to real devices. So you can think of a world where we can take that same representation and actually deploy it in production. So stay tuned for that. Cool. So here again is that tutorial link. So TFF is about having fun experimenting and building your own federated computations. We've designed it in such a way that you don't have to worry about the major pain points that we faced when developing our own federated learning system. And here's some of the pain points, like interleaving different types of logic, tension between the order of construction versus execution, and like global versus local perspectives and communication. So TFF offers two main APIs. We have the Federated Learning API, or FL API, and the Federated Core API. So the FL API is a higher level API. It provides implementations of federated training through federated averaging and evaluation that can be applied to your own existing Keras models for you to experiment with FL in simulation. This layer sits on top of the other layer, which is much more lower level and gives you more generic expressions that allow you to design and simulate custom types of computations and really control your own orchestration. So this is called the Federated Core API, which allows you to build your own federated computations. There's also local runtime simulations available. So again, there are many, many ways to get involved depending on what area of the stack interests you. This layered architecture is for a clean separation of concerns. So if you specialize in a different area, you can spend your time in the part that really interests you, whether that be the machine learning layer, compiler theory, etc. Awesome, so let's jump into the federated learning or FL API. If you'd like more details on this, here's that link. I just encourage you go into that tensorflow.org/federated, and from there you can find all the other links that I'll be presenting on today. So in order to facilitate experimentation, we've seeded the TFF repository with a few federated data sets, including a federated version of the classic MNIST dataset that contains a version of that original NIST dataset, but it's been reprocessed using Leaf so that the data itself is keyed by the original writer of the digits. Since each writer has their own unique style, this dataset will exhibit that kind of non-IID behavior expected for a federated dataset. So here's what the code looks like for TFF. We provide datasets that are pretty good proxies for those federated datasets again, and these can be accessed by using this load data function. The load data function returns a dataset, which is an instance of the tff.simulation.client data interface that allows you to enumerate a set of users to construct TF datasets that represent the data of a particular client. And this allows you to query the structure of individual elements because this is simulation. Here is where you will plug in your own Keras model. So if you have a Keras model, you can wrap it like this so it's consumable by TFF. Almost all of the information that's required by TFF can be derived from Keras interfaces. Oh, that link got off. So let's actually take a look at what a Keras model looks like. So if you're familiar with Keras already, this probably looks pretty familiar to you. Here we're just creating a simple model that will solve the MNIST example for us. We see we're creating a sequential model. It has one dense layer, and we'll be using a softmax to get our results. And here we're also attaching our loss, our optimizer, and our metrics. So now that we have a model, which we've wrapped as a TFF.learning.model under the hood for use with TensorFlow federated, we can let TFF construct a federated averaging algorithm by invoking this helper function here, tff.learning.build federated averaging process. So this is going to go ahead and construct that federated training algorithm just using a provided Keras model. So all you'd have to do on this end is provide a model, and now this will work in a federated environment on decentralized data. So let's invoke the initialize method of that iterative process we just built under the hood with that method. This will get our initial server state. Then we can call train.next, which will run a round of federated training. So this includes sending the initial server state to each of the clients. Each of the clients will run their own local round of training and send their updates back to the server. Back on the server, we'll get that aggregated new global model that's been produced from the decentralized data of each of the clients. And finally, we can think of doing federated evaluation to understand the state of our trained model. So the tff.learning.build federated evaluation will provide a federated computation for evaluation for you. And again, you can just plug in your own model function again here. That's a Keras model that's been wrapped as a tff.learning model. And then you can run evaluation using this here, and you'll get back metrics that will show you how your training is progressing. Again, that was a little bit fast. That might have been kind of overwhelming. Full tutorials are available at this link here at tensorflow.com/federated. Cool. So now let's jump into the federated core or FC API. This one is a lot lower level, so there's going to be a lot here. I hope to just kind of cover some of the general components of this. But again, this will be a lot, so I encourage you to go to that tutorial page. So the FC API is a lower level API than the FL API. It's a language for constructing distributed systems. It introduces some abstract concepts, so let's go ahead and deep dive into those concepts that are introduced by TFF. So first, I'm going to explain what a federated value is. Let's set up a scenario where we have a group of clients. In this case, each client is an individual smart temperature sensor. Each sensor is going to have its own local item of data. In this case, let's pretend it's the maximum temperature that that device saw in a single day. So you can see that, oh yeah, and this is in Celsius, by the way. So we can see that each device has seen a different maximum temperature. Each local item of the client's data has a type of float 32 because this is like a sensor reading. So we refer to all of these sensor readings collectively as a federated value or a multiset. Values like this are first-class citizens, meaning that they have a type. So here's what a federated type is. A type includes both where the value is located, which we call the placement. So all of these values are located at the clients, and the actual type of each of the local items of data. So this is float 32. So what happens now when we throw in our server into the mix? So the server will also have a value. And this value itself is float 32 at the server. This time we've dropped the curly braces to indicate that it's one value and not many values. So from all these sensor readings, how do we get our value back on the server? So let's introduce the concept now of a distributed aggregation protocol that will connect the pieces of our federated system. Let's say that it will compute the mean of all the client values to get that aggregated value back on the server. So now we've aggregated our sensor readings together to get the mean. So in TFF, we can think of a federated operation as a function, even though its inputs and its outputs live in different places. So the input to this function was all the client values that lived at the client, and then it gets us up. Hello, sorry, did I cut out for a second? Anyways, thanks for bearing with me. We provide a library of federated operators that represent the common distributed aggregations that you would use. For example, the federated average, which averages the results from the clients back to the server. I'm going to now run through a brief code example using TFF. I'm not going to go too into depth, so it might look a little confusing, but at the end, I'll be putting a link up that will lead you to the tutorials where you can walk through the code yourself. So here we'll be declaring a federated type that represents the input. And next we'll be passing this as an argument to this special function decorator that declares this a federated computation. We'll be invoking our federated operators here. So here we have that federated average intrinsic. So that was like a very simple example. So let's do a more interesting example. This time we'd like to compute what fraction of sensors have a reading over a certain threshold. So we have a threshold that we input at the server. It will be broadcast to each of the clients. So here's our first federated operator that we've introduced. This broadcast will get the value from the server to the clients. We next have a map step. You can think of this map step as the map step in MapReduce with TFF.federated_map, which will get all of our ones and zeros representing whether each client value was over the broadcasted thresholds. Then we'll perform another federated operator, which is the federated aggregation, which will get the results back on the server. So here again, we're using TFF.federated_average. So what does this look like in code? We'll again be declaring our inputs here. So here we're adding a threshold type. You can see it's a float 32, and it lives at the server. And in the body, again, we'll be invoking all of our federated operators. So here we're calling, you can see that we're calling that federated broadcast of the threshold. That's getting it to all of the client devices. We're performing a federated map set to see if individually on each of the clients, if their maximum value is over that threshold. And then we'll be doing a federated average to get that value back on the server. So here we've highlighted the local computation that each device will be performing on its own temperature reading. So this is just the computation that each device will be executing locally. Cool, that was a whirlwind introduction to the federated core API. We welcome your contributions. What you've seen here today is open source again, and it's available on GitHub. So there's those links. There's many ways to get involved. You can apply the FL API to existing ML models and data and see what happens. You can develop new federated algorithms, and you can help evolve the API itself as a foundation for TFF. For another look at the ideas we've introduced today, you can also check out this cool comic book that we have available at federated.withgoogle.com. We're really fortunate to work with two incredibly talented comic book artists to illustrate these concepts as graphic art. There's also corgis. Thanks.
Thank you, Emily, for the great talk. I think I saw a question earlier. Do you have, I think this is the question, do you have a sample project showing federated ML for mobile app using TFI? I think the keyboard example you showed is on mobile, but is there actually a sample people can look at?
Yeah, so here at Google, we actually have a federated learning system that works in production with the computations being deployed to actual devices and back. TFF currently only supports a simulation runtime. It hasn't been extended to a production environment yet. That is all TBD. Again, we do welcome contributions if that interests you. Thanks for that question.
And here's another question. Does the federated system account for active malicious users?
Oh, cool. Yeah. So this is one of the more interesting, or this is one of the very interesting areas of open research in FL, where you do try to understand like how malicious users interact with the system as a whole. There's a lot of interesting papers out there. I can somehow get those links. Maybe I can post them in that live stream chat.
Yeah, we can share links. You know, sometimes during Q&A, I said that there are some things we will share. We could either add it to the site, or we can just compile them, put it under the YouTube recording.
Yeah, that'd be super cool.
Mm-hmm.
Thanks.
Are there any other questions for Emily? Okay, great. I don't see any other questions. And thank you so much, Emily, for joining us today. We hope to see you again in our future event.
Yeah. Thanks, Margaret, for having me.
All right. Oh, I have read about GAN-based attacks. Do you think that is here's another question. Sorry.
Do you think that is a potent attack? So again, I'm one of the engineers on the team, but some of the researchers could probably give a better idea into this. That is something interesting to think about, like a GAN-based attack in a federated setting. But again, for federated learning, the idea would be to have thousands and thousands of clients that you would do this training over. So you'd have to infect such a large portion of clients that would be participating in this federated computation. It is an interesting thing to think about. I can point you at some of the papers and the research that's gone into that.
Great. Sounds great. Okay. So if there are no more questions, or we can perhaps figure out a way to connect everyone with the speaker so that if people have more questions they can ask. And thanks again for Emily, and bye.
Yeah, good to see you.
All right, so let's see. I will share my screen. Okay, so I think now we are gonna do the final raffle drawing. And is everybody ready? Like, I'm gonna just type the DevFest West Coast. Hopefully I spell it right. DevFest West Coast 2020. So before, somebody was saying that they were using the DevFest West Coast. They didn't have the 2020 at the end. So please use the right hashtag. And also somebody emailed me saying that they preferred not to have the DoorDash gift card because DoorDash is not available there. So what I'm going to do is we will do the final 2 drawing of gift cards and $25 each. And when you email the organizer alias, just specify if you prefer the DoorDash gift card or you prefer the Google Play gift card, okay? Yeah, so we use the DevFest West Coast 2020. We can only use one hashtag. We cannot pick multiple ones. So, okay. I'm going to remove all the... anyway, if you use the wrong hashtag, you could just add, like, to your stream, your tweet, just put in the correct hashtag now. All right, so import Twitter users, and the hashtag is DevFest West Coast 2020. Wow, this import is taking a bit of time. Great, so now we've got, oops, no. I did not mean to press that button. But anyway, so should we count this one? I think we should just count this one because I was going to go remove GDG Seattle before I press this button. Yeah, let's count it. All right, so this person is the first winner of this raffle. All right, so the final one. I think this person already won a previous one, so I'm sorry. I'm gonna just remove this one. I think you got it already. I thought there was a button to like remove this person from. Okay. Like usually once person gets selected. So I'm gonna run this again. This is the very last one. ShyBot7. Yay! So Shybot7, you're the last winner of today's raffle. Just contact the organizers to claim your prize. Indicate whether you prefer the DoorDash or the Google Play gift card. So with that, I am going to add all the organizers back to the screen. And let's wrap up. So I want to thank everybody for attending today's event. It's well, at least in Seattle, it's a beautiful weather out here. So instead of going out there on a beautiful Saturday, you're actually here with us listening to the talk. So really appreciate that. And most importantly, I want to thank all the speakers and organizers. Actually, you know, at the beginning, we didn't introduce us, but I think by now you already know I'm Margaret, and then we got Chris, Jerry, and Vikram, and all of you. Thank you very much. And what's next? Please join us. I have put the link here for joining the chapters, GDG Seattle. We'll add the link to GDG Portland and join GDG San Francisco, and I think there's GDG Cloud San Francisco as well, and join GDG Silicon Valley and TensorFlow Northwest. So here are some of the upcoming events. For GDG Seattle, I'm hearing an echo. You all hear an echo?
Yeah, I think it might be your YouTube feed that might be running somewhere.
My YouTube feed? Actually, I don't have a YouTube feed. I think it's somebody else. I don't have a YouTube feed. Okay, does it sound better now?
No,
Not really, but it's fine, I think.
Okay. All right, so final wrap up. For GDG Seattle, we are planning a ML model deployment study jams coming up in September 3rd, 17th, and then October 1st. Some of you have attended our previous study jam by Andy Furlich on deep learning design patterns, which was focusing on the model architecture. So this upcoming 3 sessions of study jams are focusing on more of the model deployment. And then I have added a link here about AI Week at Google Cloud Next, as well as the federated learning workshop that Emily has mentioned in her talk. So that's it. That's the end of our event.
Thank you, everybody. Yeah, it was an interesting event. We had lots of cool talks, and thank you, everybody, for joining us. Yeah.
Thanks for people.
Yeah, it was really awesome.
Yeah,
thanks.
Great.
Nice of you to spend your Saturday with us.
Yeah, exactly.
Yep. Bye, everyone.
Bye, everyone.
Bye, everybody.
Bye. Thanks.